Hello there, and welcome to Just About Earth, the quiet corner of the internet where curiosity slows its breathing, where science takes off its shoes, and where the deep past becomes a soft place to rest your thoughts. Tonight, we are not rushing anywhere. We are not chasing headlines or checking the clock. Instead, we are stepping gently backward through time, far beyond maps, beyond recorded history, beyond even the first footprints left by living things on dry land. We're drifting into a world so old that the Earth itself was still learning how to be a planet. Before we begin that long, slow journey, let me ask you something simple and personal. Where are you listening from right now? Are you tucked into bed under a blanket, sitting by a window with the night air nearby, or letting this play softly in the background as the day finally loosens its grip? And what time is it in your corner of the world at this very moment? It feels fitting, doesn't it, to think about time while we prepare to wander through billions of years of it. If you find this space calming, or if the idea of travelling through Earth's deepest memories helps you unwind, you might consider giving the video a like or subscribing. It helps this quiet little channel reach others who might also be looking for a peaceful place to land at the end of a long day. But for now, there is nothing you need to do, nowhere you need to be. Just let the story unfold at its own steady pace. Tonight's journey takes us to a time when the planet was still young in a way that is hard to truly imagine. A time before trees, before animals, before birdsong or footsteps in the soil. A time when the land itself gathered into a single enormous body, stretching across the face of the world like a vast and silent continent. That ancient world is known to us as Kenorland, Earth's first supercontinent, a name that carries the weight of a planet's earliest attempt at becoming something familiar. But rather than starting with the name or the science, let's begin with a feeling. Imagine standing somewhere that has no sign of human presence, no roads, no buildings, no distant glow on the horizon, just land, sky, and silence. Now take that idea and stretch it far beyond anything you have ever experienced. There is no grass beneath your feet, no birds overhead, no wind moving through leaves because there are no leaves to move. The ground is bare rock and dust. The air feels strange in your lungs, thinner, sharper, different in a way your body does not quite know how to handle. And the sky above you does not look like the one you know. This is not Earth as you recognize it. This is Earth before it learned how to breathe. Kenorland existed more than 2.5 billion years ago, in a stretch of time scientists call the Archean and early Proterozoic eons. Those words sound technical, but all they really mean is very, very long ago. So long ago that almost everything that once existed on the surface of the planet has been erased, recycled, melted, crushed, and reformed by the slow, patient movements of the Earth itself. What we know about Kenorland does not come from written records or ancient drawings. It comes from rocks, from minerals locked inside stone that has survived an almost impossible journey through time. These rocks are scattered across modern continents, in places like Canada, parts of Africa, Australia, and Scandinavia. They are fragments of a world that no longer exists, like torn pages from a book that was mostly burned but never completely lost. The idea of a supercontinent is, in itself, a strange one. Today we are used to seeing the world divided into separate landmasses, separated by wide oceans and named with borders and lines. But the Earth does not care about those divisions. The planet's surface is broken into massive plates that move, slowly and steadily, over the deeper, hotter layers below. Over millions of years, these plates drift, collide, pull apart, and rearrange the face of the world like an unhurried puzzle. Kenorland was one of the earliest times when many of those pieces came together into a single, vast landmass. It was not the first land to exist, but it was one of the first times Earth gathered so much of its surface into one connected whole. Picture a world where most of the dry land is part of the same continuous stretch of rock, bordered by oceans that wrap around it like a single, endless shoreline. But even that picture is still too familiar, because the land of Kenorland did not look like the continents we know today. There were no rolling green hills, no forests, no rivers cutting through soft soil. The surface was harsh, raw, and shaped mostly by fire and stone. Volcanoes were far more common and far more active than they are now. The Earth's interior still held more heat from its formation, and that heat pushed upward, cracking the crust and spilling molten rock across wide areas of the land. Instead of mountains formed by the slow collision of plates, much of Kenorland's surface was shaped by lava flows that hardened into vast, dark plains of basalt. In some places, towering volcanic structures rose above the surrounding terrain, their slopes built layer by layer from countless eruptions. These were not the gentle, scenic volcanoes you might see in a travel documentary. These were part of a restless young planet still figuring out how to release the energy trapped inside it. The sky above this ancient world told a different story as well. Today our atmosphere is rich in oxygen, which gives us blue skies and breathable air. But during the time of Kenorland, oxygen was only a trace ingredient. The air was dominated by gases like nitrogen, carbon dioxide and methane. The sunlight that filtered through this mix would have given the sky a different colour, perhaps hazy, perhaps tinted in ways we can only guess at. Clouds still formed, rain still fell, and storms still moved across the land, but everything about them was shaped by a planet that was chemically and biologically very different from the one we know. Lightning may have flashed across volcanic plains, rain may have fallen into shallow mineral-rich seas, and beneath those waters, life was already quietly at work. Because even in this harsh alien world, Earth was not empty. The life of Kenorland was small, almost unimaginably small. There were no plants, no animals, no shapes that you would recognise as living if you saw them with your own eyes. Instead, the planet was home to microscopic organisms, mostly bacteria and archaea, that lived in water and damp environments. These tiny beings formed thick, layered communities known as microbial mats, which spread across shallow coastlines and tidal flats. These mats were not just passive passengers on the planet, they were active participants in shaping its future. Some of these microorganisms had learned a remarkable trick. They could use sunlight to produce energy, much like plants do today. But in the process, they released a waste product that would eventually change the entire world. That waste product was oxygen. At first, this oxygen did not stay in the air. It reacted with iron in the oceans and rocks, forming rust-like minerals that sank to the seafloor and became part of the planet's growing layers of stone. Over millions of years, this process created massive deposits of banded iron formations, which we still mine today for the steel in our buildings, our cars, and even the devices you might be using to listen right now. It is a quiet connection, but a real one. The microbes of Kenorland helped create the materials that shape the modern world. As time passed, more and more oxygen built up in the atmosphere. This slow shift is known as the Great Oxidation Event, and it marked one of the most important turning points in Earth's history. For many of the organisms that lived without oxygen, this change was a disaster. Entire ecosystems collapsed. But for other forms of life, it opened the door to new ways of living, new ways of producing energy, and eventually, much more complex forms of biology. All of that was still far in the future during Kenorland's time, but the seeds of it were already there, drifting in shallow seas, clinging to rocky shorelines, and quietly reshaping the chemistry of the entire planet. While life worked on the air and water, the Earth itself was working on the land. The plates that held Kenorland together did not stay still. Heat rising from deep within the planet caused cracks and weak points to form. Over long stretches of time, the supercontinent began to strain and stretch. Rifts opened, letting magma rise and harden into new crust. Slowly, almost imperceptibly, the single great landmass began to pull itself apart. But before that separation was complete, Kenorland likely experienced a series of dramatic climate shifts. One of the most striking ideas in Earth science is that our planet may have gone through periods when much of its surface was covered in ice, even near the equator. These events are sometimes called Snowball Earth episodes. During Kenorland's later years, as oxygen levels rose and certain greenhouse gases were reduced, the planet may have cooled enough to trigger widespread glaciation. Imagine ice spreading across a world that already feels stark and quiet. Glaciers creeping over volcanic rock, frozen seas reflecting a dim, unfamiliar sky, microbial life clinging to survival in pockets of liquid water beneath the ice or near volcanic heat. This is not a gentle, comfortable picture, but it is a powerful one, a reminder that Earth has never been a static, stable place. It is a world of long experiments, of trial and error on a planetary scale, and yet through all of this, through fire, ice, shifting air and breaking continents, life persisted. The story of Kenorland is not just the story of a supercontinent, it is the story of a planet learning how to be habitable, learning how to build an atmosphere that protects its surface, learning how to cycle chemicals through rock, water, and living things, learning how to create conditions where complexity can slowly, patiently emerge. When you look at a modern map with its familiar shapes and names, it is easy to forget that those shapes are temporary. The continents you know are just the latest arrangement in a long sequence of planetary redesigns. Before Pangaea, before Rodinia, before any of the land masses that show up in textbooks, there was Kenorland, quietly assembling and quietly coming apart in a world that had no one to watch it happen. And now, here you are, billions of years later, listening to the echo of that ancient world through the careful study of stone and chemistry and light. It is a strange and gentle connection across time, one that reminds us that even the most distant past is still part of the story that led to this moment, to this breath, to this place where you are resting right now. Somewhere far beyond the reach of calendars, before the idea of a day meant anything more than light and dark taking turns, the Earth settled into a quiet moment of togetherness. The surface of the planet, which today is scattered into familiar continents and wide oceans, once gathered itself into a single immense stretch of land. This was not a moment anyone witnessed, not an event marked by sound or spectacle, but a slow, patient process that unfolded over millions of years, like a world exhaling and drawing itself inward. If you could drift above the planet during this distant dawn, you would not recognize the map below you. There would be no outlines that resemble the shapes we memorize in school. No Atlantic, no Pacific, no neat boundaries between land and sea. Instead, there would be a vast connected landmass surrounded by a global ocean, a single shoreline tracing the edge of a world that had not yet learned how to divide itself. Kenorland did not appear suddenly. It was the result of countless slow collisions between ancient pieces of crust called cratons. These were the oldest, most stable parts of the Earth's surface, thick slabs of rock that had survived the planet's violent early years. Over time, these cratons drifted toward one another, nudged by the slow churn of the mantle beneath them. When they met, they did not bounce away. They pressed together, welded by heat and pressure, forming the backbone of the first great continent. Imagine the sound of two enormous stone plates meeting, not with a crash, but with a deep, silent squeeze that lasts longer than entire civilizations will one day exist. That is how Kenorland came into being, not through drama, but through persistence. The land itself would have felt unfamiliar underfoot. Today, soil is rich with organic material, broken down from generations of plants and animals. On Kenorland, there was no such layer. The surface was mostly bare rock, gravel, and mineral dust. In some places, you might find thin crusts of microbial life, faintly coloured mats clinging to damp areas near water, but vast regions of the interior would have been stark and exposed. the ground would tell a story of fire. Much of Kenorland's crust was shaped by volcanic activity, with layers of hardened lava stacked like pages in a very old book. These volcanic plains, known as greenstone belts in the rocks that survive today, hint at a world where molten stone regularly reached the surface. Instead of quiet hills and winding rivers, there were fields of dark basalt and the remains of ancient eruptions, frozen in place by time. Looking toward the horizon, you would not see forests or grasslands breaking up the view. The land would stretch out in long, uninterrupted lines of rock and low, weathered ridges. In some regions, mountains would rise where craters had collided, pushed upward by the force of the meeting plates. These mountains would not look like the jagged peaks of modern ranges. Over millions of years, wind and water would have worn them down, rounding their edges and spreading their material across the surrounding plains. Water still shaped this world, even without life to help it along. Rain fell from heavy mineral-laden clouds, carving channels into the rock. Rivers flowed toward the edges of the continent, carrying dissolved metals and sediments into the surrounding ocean. Along the coasts, shallow seas lapped against stone shores, creating wide tidal flats where water and land met in a slow, daily rhythm. Those coastlines were among the most active places on the planet, not just geologically, but biologically. In the warm, shallow waters near the shore, microbial communities formed thick, layered structures called stromatolites. These were built by generations of microorganisms trapping sediment and growing upward toward the light. Over time, they created rounded, mound-like formations that could rise above the sea floor, sometimes reaching the surface of the water. If you stood near one of these ancient shorelines, you might see something that feels quietly remarkable. The water would appear still, but beneath the surface, billions of tiny lives would be working together, absorbing sunlight, exchanging chemicals, and slowly, steadily changing the makeup of the planet's atmosphere. The sky above Kenorland would not have been the clear blue we associate with a sunny day. With little oxygen and more methane and carbon dioxide in the air, the light from the sun would scatter differently. The result may have been a sky that looked hazy or tinted, perhaps leaning toward orange or grey, depending on the time of day and the mix of gases overhead. The sun itself was slightly dimmer back then, producing less energy than it does today. This is known as the faint young sun paradox. Despite the weaker sunlight, the Earth remained warm enough to support liquid water, likely because greenhouse gases in the atmosphere trapped more heat. It was a delicate balance, one that kept the oceans from freezing solid even as the planet slowly evolved. Day and night still followed one another, but the length of a day was shorter than what you experience now. The Earth was spinning faster on its axis, meaning the sun would rise and set more quickly. A full rotation might have taken only around 18 to 20 hours instead of 24. The rhythm of light and darkness was brisker, giving the world a slightly faster pulse. Standing on Kenorland, you might notice how quiet it feels. There is no rustling of leaves, no calls of animals, no buzzing of insects. The only sounds would come from wind moving across stone, waves breaking along the shore, and the distant rumble of volcanic activity. It is a world where silence feels deep and wide, stretching across both space and time, and yet beneath that quiet surface the planet is anything but still. Deep below your feet the mantle churns slowly, moving heat and material from the Earth's interior toward the surface. This movement drives the plates that hold the continent together. Even as Kenorland appears whole and solid, it is already changing, already under stress from forces that will eventually pull it apart. In some regions, the crust stretches thin, forming rift zones where the land begins to crack. These are the early signs of separation, places where magma rises and creates new rock. Over millions of years, these cracks will widen, fill with water, and become the beginnings of new oceans. But for now, Kenorland remains largely intact, a single world in a sea that wraps all the way around it. The ocean itself is not the familiar blue you might picture. Its chemistry is different, rich in dissolved iron and other minerals. In deeper waters, where oxygen has not yet reached, the sea may appear greenish or even dark, tinted by the substances carried into it by rivers and volcanic activity. When oxygen produced by microbial life meets iron in the water, it forms rust-like particles that sink to the bottom. Layer by layer, these particles settle, creating the banded iron formations that will one day be discovered and studied by humans trying to piece together this ancient story. Each band is a quiet record of a moment when the chemistry of the planet shifted, when life and rock interacted in a way that left a lasting mark. Kenorland's position on the globe is still a subject of careful study and debate. Unlike modern continents, which we can track with satellites and GPS, this ancient landmass must be reconstructed from clues locked in stone. Scientists look at the magnetic properties of rocks, which record the direction of the Earth's magnetic field at the time they formed. By comparing these records from different parts of the world, they can estimate where those pieces of crust once sat relative to one another. Through this method, a rough picture emerges of Kenorland as a sprawling continent that may have stretched across much of the planet's equatorial region. This placement would have exposed large areas of land to consistent sunlight and warm temperatures, which may have helped sustain the microbial ecosystems along its coasts. Even so, the interior of the continent could be harsh. Far from the moderating influence of the oceans, temperatures might swing more dramatically between day and night. Rain would be less frequent, and water sources more limited. In these dry, rocky regions, life would struggle to gain a foothold, making the edges of the land the true centres of biological activity. As time passes, subtle changes begin to ripple through the world. Oxygen, once quickly consumed by reactions with rock and metal, starts to accumulate in the air. The sky slowly transforms. The chemistry of the ocean shifts. Some of the microbes that once thrived find the new conditions hostile, while others adapt and flourish. This is not a smooth or gentle transition. It is a period of upheaval, of extinction and opportunity intertwined. At the same time, the climate begins to wobble. Changes in atmospheric gases alter how much heat the planet retains. In some models, this leads to episodes of intense cooling, where ice spreads far beyond the poles. Glaciers may reach into regions that were once warm and temperate, covering parts of Kenorland in thick reflective sheets of ice. Picture standing at the edge of that ancient continent as a glacier creeps forward, its surface catching the dim sunlight and scattering it back into the sky. Beneath the ice, rock is ground down into fine dust, which will later be carried into the sea when the ice retreats. This cycle of advance and retreat leaves its own marks in the geological record, another set of clues for future minds to find. Even during these colder times, the planet does not fall silent. Volcanic heat creates pockets of warmth. Beneath the ice, liquid water persists. Life, small and resilient, continues its slow work. Kenorland exists in this balance of forces, held together by the movement of plates, shaped by fire and water, transformed by the quiet labour of microscopic organisms. It is both a place and a process, a stage in the Earth's long experiment with itself. What makes this moment in the planet's history so compelling is not just that the world was physically united, but that so many of the systems we depend on today were taking their early shape. The air you breathe, the metals in your tools, the structure of the continents themselves all trace part of their story back to this time. And yet, for all its importance, Kenorland remains mostly invisible. There are no grand, intact landscapes left behind, no preserved valleys or coastlines you can visit. Only scattered fragments remain, tucked into the cores of modern continents, quietly holding their ancient memories. When you look at a piece of old stone, perhaps in a museum or along a rocky trail, it is possible that some part of it once belonged to that first great landmass. It may have been part of a volcanic plain, or a mountain route, or a shoreline where microbial mats soaked in the early sun. That thought connects the present to a world so distant it feels almost imaginary. Long before the air became something you could take for granted, before every breath arrived without a second thought, the sky above Earth told a very different story. It was still a sky, still a wide and open ceiling of light and cloud and weather, but the invisible substance filling it was not designed for human lungs, or animal lungs, or even plant leaves. It belonged to a planet that had not yet learned how to share its atmosphere with complex life. So, let's step into that ancient moment together, gently and without hurry. Imagine standing on the surface of Kenorland, the vast landmass stretching beyond the horizon in every direction. The ground beneath you is hard and bare, shaped by fire and time. The sea glimmers somewhere far away, shallow and mineral-rich. And above it all, the sky hangs heavy with a mixture of gases that would feel strange, sharp, and unsettling if you tried to breathe them in. The air during this distant era was not empty, of course. It was full, dense and active, but its ingredients were different from the ones your body depends on today. Nitrogen was already the main component, much as it is now, but oxygen, the gas that fuels your cells and keeps your brain awake, existed only in tiny traces. Instead, carbon dioxide and methane played much larger roles, drifting through the atmosphere and shaping how the planet held onto heat from the sun. If you could take a sample of that ancient air and hold it in a clear container, it would look the same as modern air. There would be no visible difference. And yet, the moment you tried to breathe it, your body would tell you that something was very wrong. The familiar ease of inhaling would be replaced by a sense of strain, of not quite getting what you need. The atmosphere of Kenorland was not built for you, or for anything like you. It belonged to a world still dominated by the smallest and simplest forms of life. The sky itself would have looked unfamiliar as well. Today, the blue colour of the daytime sky comes from the way sunlight scatters through oxygen and nitrogen molecules. With far less oxygen and more methane and carbon dioxide, the scattering would have been different. The result might have been a sky that leaned toward a hazy grey, or perhaps a soft orange tint, especially during sunrise and sunset. The light would feel muted, filtered, as if the sun were always shining through a thin veil. Clouds still formed and moved across this ancient sky, but they carried rain that was slightly acidic, shaped by the carbon dioxide dissolved in the air. When this rain fell onto the land, it reacted with the bare rock, slowly breaking it down and carrying minerals into the oceans. This process, known as weathering, played a quiet but powerful role in shaping both the land and the chemistry of the seas. Every drop of rain was part of a slow, planet-wide conversation between sky, stone, and water. The sun, meanwhile, was younger and slightly dimmer than the one you see today. It produced less energy, which should have left the Earth frozen, but the thick blanket of greenhouse gases in the atmosphere trapped enough heat to keep the oceans liquid and the surface warm enough for life to persist. It was a delicate balance, one that could shift with changes in volcanic activity, chemical reactions in the oceans, or the slow work of living organisms. And living organisms were already busy. Along the edges of the ancient seas in shallow sunlit waters, microbial communities formed layered structures that rose slowly from the seafloor. These stromatolites were not just passive piles of sediment, they were living systems, built by generations of tiny cells working together, trapping particles and growing upward toward the light. Some of these microbes had learned how to use sunlight in a remarkable way. Through a process known as photosynthesis, they captured energy from the sun and used it to turn carbon dioxide and water into sugars they could use for growth. But this process produced a byproduct that would eventually transform the entire planet. That byproduct was oxygen. At first, the oxygen released by these microbes did not linger in the air. The world around them was full of substances eager to react with it. Iron dissolved in the oceans, sulfur in the rocks, and gases in the atmosphere quickly absorbed the new oxygen, locking it away in minerals and sediments. This is why the early sky remained largely free of oxygen for so long, even as life continued to produce it. You can think of the planet as a vast sponge at this stage, soaking up oxygen as fast as it appeared. Over time, this sponge began to fill. The iron in the oceans rusted and sank, forming thick layers on the seafloor. The rocks on land absorbed what they could. Slowly, very slowly, the balance began to shift. There came a point when the Earth could no longer hide all of the oxygen being made. That is when the gas started to accumulate in the atmosphere. This transition is known as the Great Oxidation Event, and it marks one of the most profound changes in Earth's history. But from the perspective of standing beneath that ancient sky, the change would not have been dramatic or sudden. There would be no moment when the air suddenly became breathable, no clear line between before and after. Instead, it would feel like the planet was slowly exhaling, releasing something new into the space above its surface. As oxygen levels rose, the chemistry of the sky began to change. Methane, which had been a powerful greenhouse gas, reacted with the new oxygen and broke down. With less methane to trap heat, the planet began to cool. This shift may have contributed to periods of widespread glaciation, when ice spread across large portions of the land and sea. So, in a quiet and indirect way, the tiny microbes along the coastlines of Kenorland may have helped trigger some of the coldest episodes in Earth's deep past. The sky during these colder times would have looked different again, with ice reflecting sunlight back into space and fewer greenhouse gases holding warmth near the surface. The atmosphere would feel sharper, clearer, and colder. Clouds might carry snow instead of rain. The land, already bare and stark, would take on a bright frozen stillness in many regions. But even as the climate shifted, the oxygen in the air continued its slow rise. For the organisms that had evolved in a world without oxygen, this new gas was not a gift. It was a poison. Oxygen is highly reactive, and for many early life forms it damaged their internal chemistry. Entire groups of microbes likely vanished as the atmosphere changed around them, unable to adapt to the new conditions. At the same time, oxygen opened the door to new possibilities. Some organisms learned to use it as part of their energy-making process. This method, known as aerobic respiration, is far more efficient than the older oxygen-free pathways. It allows cells to extract much more energy from the same amount of food. This extra energy would eventually support larger, more complex forms of life. But during the time of Kenorland, this future was still distant. For now, the world remained mostly microscopic, its greatest changes unfolding at scales too small to see with the naked eye. The sky, however, was beginning to develop another important feature. With enough oxygen in the upper atmosphere, sunlight could break apart oxygen molecules and allow them to form ozone. This ozone layer acts as a shield, absorbing harmful ultraviolet radiation from the sun. Before it existed, the surface of the planet was exposed to much stronger radiation, which made life on land extremely difficult. As the ozone layer slowly took shape, it created a safer environment near the surface. This protection would one day make it possible for life to leave the water and explore the land. But during Kenorland's era, this was still a promise rather than a reality. The land remained largely empty, its surface shaped by weather and geology rather than roots and footsteps. If you were to lie back on the bare rock and look up at the sky during this time, you might notice how wide and untouched it feels. There are no aircraft crossing overhead, no faint glow from distant cities, no satellites tracing silent paths across the night. The stars, when they appear, shine with a clarity that is difficult to find in the modern world. The moon, closer to Earth than it is now, would appear slightly larger in the sky. Its gravitational pull would drive stronger tides, causing the oceans to rise and fall more dramatically along the shores of Kenorland. These tides would wash over microbial mats, exposing them to air and sunlight, then covering them again, creating a dynamic environment where life and chemistry constantly interacted. Every tide cycle was another chance for oxygen to escape into the air, another small step in the long transformation of the atmosphere. Volcanoes also played their part in shaping the sky. Eruptions released clouds of gas and ash, adding carbon dioxide, sulfur compounds, and other materials to the air. Some of these gases warmed the planet, others cooled it by reflecting sunlight. The balance between these forces helped drive swings in climate that would last for millions of years at a time. Standing near an active volcanic region, you might see plumes rising into the sky, spreading out like dark, slow-moving clouds. The air would smell sharp and metallic, filled with the scent of sulfur. Ash would settle on the land and into the sea, providing fresh minerals that could fuel microbial growth along the coast. In this way, even the most violent processes on the planet became part of the quiet partnership between life and atmosphere. The sky above Kenorland was not just a passive backdrop. It was a living system, constantly changing in response to what happened on the surface and in the oceans below. Gases moved between air and water, chemicals reacted with rocks, life altered the composition of everything it touched. This interconnectedness is one of the most striking features of Earth's story. The planet does not operate in separate layers that ignore one another. The sky, the sea, the land, and the living world are all tied together, each shaping the others over time. As oxygen continued to build, the sky gradually became more like the one you know. The scattering of sunlight shifted. The colour of daylight edged closer to blue. The chemistry of rain changed. The balance of gases moved toward a mixture that could support more active, energy-hungry forms of life. But this process took hundreds of millions of years. It was not a smooth climb, but a series of steps forward and back, influenced by volcanic bursts, climate swings, and the slow movement of continents. Through it all, Kenorland remained a quiet witness, its vast surface exposed to a sky that was learning how to become something new. If you pause for a moment and think about your own breath, about how naturally it comes to you, it is worth remembering how unusual that ease is in the long history of the planet. For most of Earth's existence, the air was not something you could simply breathe. It had to be made, shaped, and adjusted by countless generations of tiny organisms working in the background. Every inhale you take carries a trace of that ancient labour. As the atmosphere became richer in oxygen, the stage was slowly being set for a world that could support plants, animals, and eventually, thinking beings who would look back and wonder about their origins. The sky without oxygen was giving way to a sky that could hold clouds of water vapour, shield the surface from harsh radiation, and sustain a complex web of life. Long before the oceans became the deep blue expanses you picture on maps and globes, before waves reflected the sky like polished glass, the seas of Earth told a very different story. They were still vast, still restless, still shaped by wind, tides, and the pull of the moon, but their colour, their chemistry, and even their role in the planet's life were unfamiliar in ways that are easy to overlook when you stand at a modern shoreline. So let's ease ourselves into that ancient water, not by diving in all at once, but by standing quietly at the edge of Kenorland's coast, watching the tide move in and out over rock that has never known a footprint. The air above is hazy, the sky carries a muted light, and the sea in front of you does not shine with the clear, bright blues of today. Instead, its surface holds a darker, heavier tone, sometimes greenish, sometimes shadowed, sometimes reflecting the minerals and metals dissolved within it. The oceans of this distant world were not just bodies of water. They were vast chemical laboratories, constantly mixing elements from the air, the land, and the planet's interior. Every wave that rolled toward the shore carried more than just water. It carried iron, sulfur, silica, and a long list of dissolved substances that shaped both the colour of the sea and the future of life itself. If you were to scoop up a handful of this ancient seawater and let it sit in the light, you might notice a faint tint, a hint that something more than salt was suspended within it. Much of that colour would come from iron, which was far more abundant in the oceans during this time than it is now. Without large amounts of oxygen in the water or the air, iron stayed dissolved instead of forming solid rust particles that sink to the bottom. This gave the seas a heavier, murkier appearance, especially in deeper regions where sunlight struggled to reach. The clear, transparent blues of modern oceans rely on water that is relatively free of large amounts of dissolved metals. Kenorland seas had no such clarity. They were rich, thick with chemistry, and constantly changing in response to what flowed into them from the land and rose into them from the deep. Rivers played a quiet but powerful role in this process. Rain falling on the bare, rocky surface of Kenorland picked up minerals as it moved, carrying them downhill and toward the coast. Without plants to hold the soil in place, erosion happened more easily. Sediments washed into the ocean in broad, steady streams, spreading out into shallow coastal waters and settling on the seafloor. Along these shores, wide tidal flats formed, places where land and sea blurred into one another. At low tide, vast stretches of wet rock and sediment lay exposed to the air and the sun. At high tide, those same areas were covered again, becoming shallow pools that warmed quickly and cooled just as fast. These changing conditions created perfect environments for microbial life to thrive. In these shallow waters, life and chemistry met in some of the most important ways the planet had ever seen. Microbial mats spread across the seafloor and over rocks near the coast, forming layered communities that could stretch for meters at a time. These mats trapped sediment, held moisture, and created tiny pockets of different chemical conditions within their layers. Some parts of the mat were exposed to oxygen and sunlight, others were dark, low in oxygen, and rich in different compounds. This variety allowed different types of microbes to coexist, each performing its own small role in a larger system. Some used sunlight to produce energy, others fed on the waste products of their neighbours. Together they formed living carpets that slowly grew upward, creating rounded, mound-like structures that rose from the seabed. These stromatolites were more than just signs of life. They were active builders of the planet's chemistry. As oxygen-producing microbes worked in the upper layers of these mats, they released oxygen into the surrounding water. The moment this oxygen met the iron dissolved in the sea, a reaction occurred. The iron oxidized, forming tiny rust particles that clumped together and sank to the bottom. Over time, these particles settled into thin layers, alternating with layers of other sediments. This slow, repetitive process created what are now known as banded iron formations, some of the most striking geological records of this era. Each band tells a story of a moment when oxygen levels rose, iron reacted, and the chemistry of the ocean shifted. Layer by layer, the seafloor became a quiet archive of the planet's changing atmosphere. Standing at the edge of the ancient sea, you would not see these layers forming. The process was far too slow, far too subtle. But over millions of years, the ocean floor thickened with these deposits, locking away enormous amounts of iron and oxygen in solid rock. This had a ripple effect. As more iron was removed from the water, the ocean slowly became less murky. With fewer metals to absorb and scatter light, sunlight could penetrate deeper into the sea. This change allowed photosynthetic microbes to expand into new areas, spreading beyond the shallowest coastal zones and into slightly deeper waters. The ocean, in this way, was not just reacting to life. It was shaping where life could go and how it could grow. The deeper parts of the sea, however, remained very different from the sunlit shallows. Without oxygen reaching these depths, the water there stayed dark and chemically distinct. Sulfur compounds and other reduced chemicals accumulated, creating conditions that would be hostile to most modern organisms. These deep waters likely had a strong, sharp smell, something like rotten eggs, produced by hydrogen sulfide gas released by certain types of bacteria. Currents still moved through these ancient seas, driven by differences in temperature and salinity. Warm water near the surface flowed toward cooler regions, while colder, denser water sank and moved along the ocean floor. This circulation helped distribute heat and chemicals around the planet, linking distant regions in a slow, steady exchange. The Moon's closer orbit added another layer of movement. Tides rose higher and fell lower than they do today, pulling water farther onto the land and then back again. This constant motion washed over microbial mats, exposed them to air, then submerged them again, creating cycles of stress and opportunity that encouraged resilience and adaptation. If you watch the tide come in along a Kenorland shoreline, you would see water spreading across wide, flat areas of rock, filling shallow basins and channels. As the water warmed in the sunlight, chemical reactions would speed up. Gases dissolved more easily. Minerals interacted with the microbes living on the surface. When the tide retreated, some of that water remained behind in isolated pools, slowly evaporating and leaving behind concentrated salts and minerals. These small, temporary bodies of water became hotspots for chemical activity. Conditions could change quickly, pushing microbes to adapt or die. Over time, this constant challenge may have encouraged the development of new metabolic pathways, new ways for life to use the materials around it. The colour of the sea would shift with these changes. In some areas, greenish tones might dominate, influenced by iron and microbial pigments. In others, the water might appear darker, almost black, where deep, oxygen-poor currents rose closer to the surface. After large volcanic eruptions, ashen minerals could spread across the ocean, briefly altering its appearance and chemistry on a regional or even global scale. Volcanoes, both on land and beneath the sea, were important contributors to the ocean's makeup. Underwater eruptions released hot, mineral-rich fluids into the surrounding water, creating hydrothermal systems similar to the deep-sea vents found today. These areas were rich in chemicals like hydrogen, methane and sulfur, providing energy sources for microbes that did not rely on sunlight. In the darkness near these vents, life followed a different path. Instead of drawing energy from the sun, these organisms use chemical reactions to fuel their growth. This type of life, known as chemosynthetic, formed the base of small ecosystems that thrived in places where light never reached. Even in Kenorland's time, the ocean was a patchwork of environments, each with its own rules and possibilities. The interaction between the sea and the atmosphere added another layer of complexity. Gases moved freely between air and water. Carbon dioxide dissolved into the ocean, forming carbonic acid, which influenced the pH of the water and affected how minerals formed and dissolved. Oxygen, once it began to appear in larger amounts, also moved into the sea, changing the chemistry of surface waters. This exchange helped regulate the planet's climate. When more carbon dioxide was absorbed by the ocean, less remained in the air to trap heat. When volcanic activity released large amounts of gas, the balance shifted again. The ocean acted as both a buffer and a participant in these changes, smoothing out some of the extremes while amplifying others. Over long periods, these processes shaped the climate in ways that could lead to dramatic shifts. As greenhouse gases were reduced and sunlight reflected by ice and clouds increased, the planet could cool enough to trigger widespread glaciation. During these colder times, large portions of the ocean's surface may have been covered in ice, especially near the poles and possibly even closer to the equator. Underneath this ice, liquid water still flowed. The deep ocean remained active, circulating heat and chemicals. Life retreated into protected zones, near hydrothermal vents or beneath thinner ice where sunlight could still penetrate. When the ice eventually melted, fresh water poured into the seas, changing their salinity and stirring up sediments that had been locked away for millions of years. This reset the chemical stage once again, creating new conditions for life to respond to. The ancient oceans were not static backdrops. They were dynamic systems, constantly reshaped by the movement of continents, the rise and fall of mountains, and the slow breaking apart of Kenorland itself. As the great landmass began to crack and rift, new coastlines formed. Fresh seawater flooded into newly opened basins, creating young oceans that were shallow, warm and rich in nutrients. These new environments became centres of biological activity, places where microbial communities could spread and diversify. Each new shoreline added more interaction between land and sea, more weathering, more minerals, more opportunities for chemical reactions that could influence the atmosphere above and the rocks below. From a distance, all of this might look calm. The surface of the ocean rises and falls, clouds drift overhead, the sun traces its path across the sky. But beneath that surface, the planet is engaged in a slow, complex dance, one that ties together water, stone, air and life into a single evolving system. If you take a moment now to think about the modern ocean, its deep blues and wide horizons, it can be easy to forget how much of its character was shaped in this distant past. The balance of salt, the presence of oxygen, the clarity of the water, and even the types of life it supports all trace part of their story back to these early chemical experiments carried out on a planetary scale. Every wave you hear today carries an echo of those ancient seas. Across the wide, unbroken surface of the ancient world, the land stretches outward in a way that feels almost endless. There is no canopy overhead, no shade cast by leaves or branches, no soft ground beneath your feet. Every direction offers the same quiet expanse of stone, dust and hardened lava, shaped by time rather than by roots or paws or hands. This is Kenorland's interior, a place where the idea of a forest has not yet been invented by the planet. Let's imagine moving through this world slowly, not as a traveller in a hurry, but as someone with nothing to chase and nowhere to be. The ground underfoot is firm and uneven, a mosaic of fractured rock, gravel and mineral crusts that crunch faintly when disturbed. There is no path because there has never been a reason for one to exist. The land has never been worn smooth by repeated footsteps or the passing of herds. It has only known the long, steady work of wind, rain, and the occasional tremor from deep within the earth. The air feels different here, away from the moderating influence of the ocean. It is drier, sharper, and carries the faint metallic scent of stone and minerals. When the wind moves across the surface, it does not whisper through leaves or bend grass. Instead, it slides over bare rock and open plains, lifting fine dust into the sky and carrying it in slow, drifting clouds that settle back down miles away. Above you the sky is wide and unobstructed. Nothing breaks the line between the horizon and the clouds. The sun rises and sets faster than it does in your world, marking shorter days and nights. Its light falls directly onto the exposed land, warming the rock during the day and leaving it to cool quickly once darkness arrives. This creates strong swings in temperature, especially far from the coast, where water can no longer soften the extremes. During the warm part of the day, the surface of the land can grow hot enough to shimmer faintly in the distance. Heat waves ripple above the rock, blurring the edge of the horizon. At night, the same ground releases that heat back into the air, and the temperature drops, sometimes sharply. Without plants to trap warmth near the surface, the land responds quickly to the changing light, rising and falling in a temperature like a slow, steady breath. The shape of the terrain tells a story written by fire and pressure. In many places, wide plains of dark basalt stretch outward, formed by ancient lava flows that once spread across the surface and cooled into solid rock. These plains are broken by ridges and low mountains, where pieces of crust collided and folded long ago. Over millions of years, rain and wind have worn these features down, rounding their edges and carrying their material away in fine layers of sediment. You might come across broad, shallow valleys carved by rivers that no longer flow. In Kenorland's time, water still moved across the land, but without plants to stabilise the soil, river channels shifted often. When rain fell heavily, water rushed across the surface, picking up loose material and carving temporary paths toward the sea. During drier periods, these channels could dry out, leaving behind winding scars in the rock. Occasionally, you might notice patches of colour on the ground, subtle and easy to miss. These are not plants in the way you would recognise them. They are thin films of microbial life, clinging to damp areas where water lingers after a rain, or near the edges of shallow pools. These organisms form crusts that can be green, brown, or even purplish, depending on the types of microbes present and the chemicals they interact with. These small, quiet patches represent the only visible sign of life in a vast landscape that otherwise feels empty. There are no moving shadows, no sudden sounds, no signs of animals passing through. The silence is not just the absence of noise, it is the absence of activity at any scale large enough to catch your eye. Yet beneath this stillness, the land is far from lifeless. Below the surface, the planet remains active. Heat from the mantle pushes upward, creating zones where the crust is thinner and more fragile. In some areas, cracks form, long fractures that stretch for kilometres. These are rift zones, early signs that the great supercontinent is under strain. If you stand near one of these zones, you might feel a faint warmth rising from the ground, a subtle reminder that molten rock is not far below. In some places, this heat escapes more dramatically. Volcanoes rise above the plains, their slopes built from layers of hardened lava and ash. Some of these volcanoes are quiet, their last eruptions lost to deep time. Others remain active, releasing plumes of gas and occasional flows of molten rock that spread slowly across the land. The presence of volcanoes adds another texture to the environment. The air near them carries a sharp, sulphurous smell. The ground is coated in fine ash that settles after eruptions, creating soft, powdery layers on top of harder rock. Rain falling on this ash can form shallow, muddy pools that temporarily host microbial life before drying out again. These volcanic regions also provide some of the most chemically rich environments on land. Minerals brought up from deep within the earth become available at the surface, offering energy sources for microbes that can use chemical reactions instead of sunlight to survive. In this way, even the most dramatic features of the landscape become part of the quiet, ongoing story of life and chemistry. As you move farther inland, away from the coasts and rivers, signs of water become rarer. The land grows more uniform, more barren. Dust settles in low spots, forming thin layers that can be lifted again by the wind. Small stones click and shift when temperature changes cause the rock to expand and contract. Without plants to hold the soil together, erosion works quickly when rain does fall. Water flows across the surface instead of soaking in, carrying away loose material and leaving behind channels that can deepen with each storm. Over long periods, this process reshapes the land, carving gentle slopes and broad basins. The sky often reflects this dryness. Clouds form, but they do not always deliver rain. When they do, the storms can be brief and intense, dumping large amounts of water in a short time. These sudden downpours create flash floods that race across the land, filling dry channels and sweeping sediment toward the sea. In the aftermath of such a storm, the land changes in small but noticeable ways. Fresh layers of sediment settle in low areas. Mineral crusts left behind by evaporating water form thin, pale patterns on the surface. These patterns can crack and curl as they dry, creating a delicate, brittle texture that covers the ground until the next wind or rain event breaks it apart. The light during these moments can feel different as well. When the air is heavy with moisture and dust, sunlight scatters in soft, muted tones. Shadows lose their sharp edges. The world takes on a hazy appearance, as if seen through a thin veil. Night brings its own character to this bare landscape. With no vegetation or clouds to trap heat, the ground cools quickly. The air becomes crisp. The stars emerge with a clarity that feels almost overwhelming. The sky stretches wide and deep, filled with points of light that seem closer and more numerous than they do in your own world. The moon, larger in the sky than it is today, casts a pale glow across the plains. Its light reflects off the rock and dust, creating a soft silvery landscape where every ridge and depression stands out in gentle contrast. The stronger tides it produces can be felt even far inland, not as a movement of water, but as a subtle pull that affects the entire planet, adding a quiet rhythm to the shifting of land and sea. Standing in this place, you might feel a sense of scale that is difficult to find in the modern world. There are no familiar landmarks to measure distance by, no trees, no buildings, no signs of human presence. The horizon is defined only by the curve of the land and the meeting of earth and sky. Time itself feels different here, not because it moves more slowly, but because there is so little to mark its passing. Without seasons defined by changing leaves or migrating animals, the main signals of change come from the sky and the weather. A storm alters the surface. A volcanic eruption adds a new layer of ash. A river shifts its course. These are the moments that stand out against the long stretches of quiet. Even the growth of microbial life on land happens at a pace that is hard to notice. Thin films spread and retreat with the availability of moisture. Crusts form and break apart. Over years, over centuries, over millions of years, these small changes add up. But in any single moment, the land appears still. The absence of forests also means the absence of one of the most powerful forces in shaping modern landscapes. Today, plant roots break apart rock, stabilize soil, and create complex networks that guide the flow of water. On Kenorland, none of that exists yet. The land is shaped almost entirely by physical and chemical processes rather than by biological ones. This gives the terrain a simpler, more direct relationship with the elements. Rain falls, rock breaks down, sediment moves, wind carries dust, heat rises from below. There is a straightforwardness to the system, a clarity in how cause and effect play out across the surface. And yet, even in this simplicity, the seeds of future complexity are present. The minerals exposed on the surface will one day become nutrients for plants that do not yet exist. The oxygen slowly building in the atmosphere will eventually make it possible for larger organisms to breathe. The breaking apart of the supercontinent will create new coastlines, new shallow seas, and new environments where life can experiment and expand. The bare land of Kenorland is not an endpoint. It is a beginning. If you pause and listen in this imagined place, the quiet is not empty. It is full of distant sounds carried by the wind, the low rumble of volcanic activity far away, the faint rush of water in a temporary channel after a storm, the soft hiss of dust moving across stone. These are the background notes of a planet in motion, even when nothing seems to be happening. Kenorland remains a world of stone and sky, of fire below and wind above, of quiet processes unfolding at a pace that defies easy understanding. Walking across this bare and silent supercontinent is less about travelling through space and more about stepping into a moment in the planet's long memory, a time when the land itself was still waiting to be discovered by the life it would one day support. Beneath the stillness of Kenorland's wide, open surface, something is always moving. The ground may look solid and unchanging. The horizon may stretch out in calm, unbroken lines of rock and sky. But far below that quiet exterior, the planet is restless. Heat rises, rock softens, pressure builds. The world, even in its earliest age, refuses to sit still. To understand this ancient land, it helps to think of it not as a fixed place, but as a slow, ongoing process. The supercontinent is not simply resting on the planet's interior. It is floating on it, carried by massive plates of crust that drift atop hotter, denser material below. These plates move at a pace that feels almost imaginary to a human sense of time, no faster than fingernails grow, yet over millions of years, that gentle motion can rearrange the face of the world. Kenorland exists during a period when the Earth still holds more of its original heat. The planet has not yet cooled into the quieter, more stable state you know today. That extra heat makes the mantle more active, more fluid, more eager to push upward against the crust. As a result, volcanic activity is more common and the boundaries between plates are more dynamic. If you were to stand on this ancient land and listen, not just with your ears but with your imagination, you might sense the deep, distant hum of the planet's interior. It is not a sound you can hear, but a presence you can feel, a reminder that the ground beneath you is part of a much larger moving system. In some regions, the crust is thick and stable, built from the ancient cratons that form the core of the supercontinent. These areas are relatively quiet, shaped mostly by erosion and weather. But in other places, the crust thins and stretches. Here, the mantle presses closer to the surface, and the land responds by cracking. These cracks can begin as narrow fractures barely visible at first. Over time, as heat and pressure continue their work, the fractures widen into long rift valleys that can run for hundreds or even thousands of kilometers. The ground on either side slowly pulls apart, creating space for molten rock to rise from below. When that magma reaches the surface, it spreads out in glowing sheets, flowing across the land before cooling into solid stone. Layer by layer, these lava flows build up wide plains of basalt, dark and dense, covering older rock beneath them. This process can repeat many times in the same region, creating thick stacks of volcanic material that record the history of the planet's internal activity. These volcanic plains are not small, isolated features. Some of them can cover areas larger than entire modern countries. From a distance, they appear as vast, flat expanses of dark rock, broken only by cracks, ridges, and the occasional volcanic cone rising above the surface. Closer to an active region, the landscape takes on a more dramatic character. The ground may be warm to the touch. Fumaroles, small openings in the crust, release wisps of gas that drift into the air, carrying the sharp scent of sulfur. The rock around these vents is often stained in bright colours, yellows, reds and whites, created by minerals crystallizing as hot gases cool. Volcanoes themselves vary in shape and behaviour. Some build tall, steep-sided cones from layers of ash and hardened lava. Others spread out in broad, gently sloping forms, created by thin, fluid lava that can travel long distances before cooling. These shield-like volcanoes can grow to enormous sizes, dominating the surrounding landscape. Eruptions during this time are not always explosive. Often, lava simply wells up from long cracks in the ground and pours out steadily, forming rivers of molten stone that move slowly across the surface. As they cool, they crack and wrinkle, creating textures that can be preserved in the rock record for billions of years. Ash from more violent eruptions can spread far beyond the volcano itself. Fine particles rise into the sky and drift with the wind, settling over wide areas of land and sea. This ash layer adds a new chemical component to the surface, enriching soils that do not yet exist, and altering the chemistry of shallow waters where it eventually falls. Rain interacts strongly with these fresh volcanic deposits. Water percolates through the ash and fractured rock, dissolving minerals and carrying them into rivers and toward the ocean. This process feeds the ancient seas with nutrients and metals, linking the fiery interior of the planet to the quiet microbial life along the coasts. The movement of the crust does not only create volcanoes, it also shapes the larger structure of the supercontinent itself. Where plates collide, the land is forced upward, forming mountain ranges. These mountains are not the sharp, dramatic peaks you might associate with younger ranges like the Himalayas. Over time, erosion wears them down, smoothing their profiles and spreading their material outward into surrounding plains. Even so, these ancient highlands can still influence the flow of rivers and the patterns of weather across the land. In places where plates slide past one another, the crust can be broken into complex networks of faults. These faults create zones of weakness where earthquakes can occur. During Kenorland's time, seismic activity is likely common in many regions, releasing built-up stress in sudden shifts of the ground. if you were present for one of these events, you might feel the land tremble beneath your feet, a deep, rolling motion that passes through the rock like a wave. Cracks might open, stones might tumble from ridges, dust could rise into the air in thin, drifting clouds. These moments are brief compared to the long stretches of quiet, but they leave lasting marks on the landscape. New fractures form, old ones widen. The shape of the land changes, even if only slightly, in response to the release of pressure from deep within the planet. The ocean floor is not immune to this restless motion either. Beneath the ancient seas, long chains of volcanic ridges mark places where new crust is being formed. Here, molten rock rises from the mantle and cools as it meets the cold water above, creating fresh seafloor that slowly spreads outward on either side. This process, known as seafloor spreading, is one of the ways the planet recycles its surface. Old crust is eventually pushed down into the mantle at subduction zones, where it melts and becomes part of the deep interior again. New crust takes its place, carrying with it the chemical signature of the mantle from which it came. During Kenorland's era, these processes help maintain the balance between land and sea. As parts of the supercontinent begin to stretch and thin, new ocean basins can form. Water floods into these low areas, creating young seas that expand over time. This gradual opening of oceans marks the beginning of the supercontinent's eventual breakup. But in this moment, the process is still in its early stages. The land remains largely connected, even as it strains under the forces acting upon it. Volcanic activity also plays a role in shaping the planet's atmosphere. Gases released during eruptions include carbon dioxide, water vapour, sulfur compounds, and other materials that can influence climate. Large bursts of volcanic gas can temporarily warm the planet by increasing the greenhouse effect. Ash and sulfur particles can have the opposite effect, reflecting sunlight and causing cooling. These shifts do not happen overnight. They unfold over long periods, creating cycles of warming and cooling that can last for millions of years. During some of these colder phases, ice spreads across parts of the land and sea, adding another layer of interaction between the surface and the atmosphere. The relationship between fire and ice, between heat rising from below and cold settling from above, becomes one of the defining features of the planet's climate during this time. Life, small and resilient, adapts to these changes in its own quiet way. Microbial communities near volcanic regions often find new opportunities. The chemicals released by hot springs and vents provide energy sources that do not depend on sunlight. In these places, life can thrive even in darkness, building ecosystems around chemical reactions rather than photosynthesis. Along the coasts, ash and mineral-rich runoff from volcanic land feeds the shallow seas, encouraging the growth of microbial mats. These mats, in turn, continue their slow work of producing oxygen and altering the chemistry of the water and air. In this way, the restless crust and the living surface become partners in shaping the future of the planet. The deep interior provides the raw materials and energy. Life responds, adapts, and feeds back into the system, influencing everything from climate to ocean chemistry. The scale of these interactions is difficult to fully grasp. A single volcanic eruption might last days or weeks. A rift might take millions of years to widen into an ocean. A mountain range might rise and erode over hundreds of millions of years. Each process operates on its own timeline, yet all are woven together into the same ongoing story. From the perspective of standing on the surface, much of this movement is invisible. The land appears solid, the horizon remains steady, the sky changes with the passing of day and night. But beneath that calm exterior, the planet is constantly reshaping itself. If you place your hand on the ground in this imagined world, you might feel only cool stone or warm dust. But beneath that thin surface lies a vast dynamic system of moving rock and flowing heat that has been active since the planet first formed. The idea of a supercontinent can sometimes suggest something stable and permanent, a grand, unchanging feature of the world. Kenorland reminds us that even the largest structures on the planet are temporary. They come together, they hold for a time, and then they begin to pull apart, guided by forces far deeper and more powerful than anything on the surface. As cracks widen and new volcanic regions appear, the shape of the land starts to shift in subtle ways. Coastlines change, rivers find new paths, shallow seas form in low-lying areas. Each of these changes creates new environments, new combinations of water, rock, and chemistry for life to explore. The future of the planet is being written in these moments of slow movement and sudden release, in the steady rise of magma and the quiet settling of ash, in the gradual opening of basins and the patient erosion of mountains. And as Kenorland continues its long, slow transformation, the world above the crust responds. The oceans adjust to new shapes and depths. The atmosphere shifts with the gases released from below. Life follows the changing contours of land and sea, finding places to grow in the spaces left behind. What feels like a world of stone and silence is in truth a world of constant motion, a planet in the middle of an unending conversation between its deep interior and its living surface. Light touches the surface of Kenorland in a way that feels both familiar and strange. The sun still rises. It still climbs across the sky. It still sets beyond a distant horizon of bare rock and open land. But the rhythm of this motion carries a different tempo than the one you live by now. The planet beneath your feet is turning, yes, but it is not turning at the same pace it will one day settle into. Time itself, measured by the length of a day, is in the middle of a very long transformation. If you pause in this ancient world and watch the sun's path from morning to evening, you might notice that it seems to move a little faster across the sky. The arc from dawn to dusk feels slightly compressed, as if the planet is eager to spin and show the sun a new face sooner than expected. During Kenorland's era, a full rotation of Earth likely took only around 18 to 20 hours, not the 24 you're used to. The days were shorter, the nights followed more quickly. The pulse of light and darkness beat at a brisker pace. This faster spin is a quiet reminder that the Earth and the Moon are still adjusting their long gravitational relationship. The Moon, closer to the planet than it is today, pulls more strongly on the oceans. Those stronger tides drag against the seafloor and the continents, acting like a brake on the planet's rotation. Over billions of years, this process slowly transfers energy from Earth's spin to the Moon's orbit, pushing the Moon farther away and lengthening the day. In the time of Kenorland, that braking process is still well underway. The Moon looms larger in the sky. The tides rise higher and fall lower. The Earth turns a little faster with each cycle of light and dark. From the surface, this creates a world where the sun's presence feels more fleeting. Morning arrives, and before the land has fully warmed, the light is already beginning its slow descent toward evening. Shadows stretch and shift more quickly. The cooling of night comes sooner, and the chill settles in across the bare rock. Yet even within this shorter day, the sun remains a powerful force. Without forests or thick vegetation to absorb and scatter its rays, sunlight falls directly onto stone, dust, and shallow water. During the day, the surface heats rapidly. Rocks soak up warmth. Pools left behind by retreating tides grow warmer, sometimes hot enough to change the chemical reactions happening within them. Microbial mats living in these shallow waters respond to this daily cycle, becoming more active in the warmth and slowing down as the light fades. This daily rhythm shapes life in subtle but important ways. The shorter cycle of light and dark means that organisms adapted to this world experience more frequent transitions. Instead of a long steady day followed by a long steady night, they live through quicker shifts, adjusting their internal processes to keep pace with the spinning planet. The sun itself is also different. Younger and slightly dimmer, it delivers less energy to the Earth than it does now. This might suggest a colder world, but the atmosphere, rich in greenhouse gases like carbon dioxide and methane, traps much of the heat that does arrive. The result is a climate that can remain warm enough for liquid water to exist across much of the surface. This balance is delicate. Small changes in atmospheric chemistry, volcanic activity, or the reflectivity of the planet's surface can tip the scale toward warming or cooling. During Kenorland's time, these shifts happen over long periods, creating stretches of relatively stable conditions punctuated by episodes of dramatic change. Seasons too exist in this ancient world, though they do not yet look like the ones you recognise. The Earth's axis is tilted just as it is today, meaning that different parts of the planet receive varying amounts of sunlight throughout the year. This tilt creates cycles of longer and shorter days, warmer and cooler periods, even in a world without trees to change colour or animals to migrate. On Kenorland, the signs of seasonal change are written in temperature, rainfall and the movement of ice. In warmer periods, shallow seas expand. Rain falls more frequently in some regions, feeding rivers that carry minerals from the interior of the continent to the coasts. Microbial life along shorelines flourishes in these conditions, spreading across newly wetted surfaces and building thicker mats. During cooler periods, rainfall decreases in some areas. Glaciers may form in higher latitudes or at higher elevations, slowly creeping outward and grinding the rock beneath them into fine sediment. When these glaciers retreat, they release that sediment into rivers and seas, altering the chemistry of the water and the shape of the land. The length of a year is also changing during this time, though not in the way a human calendar would easily track. As the moon slowly moves away from Earth, the number of days in a year increases. In the era of Kenorland, there are more days in a year than there are now, simply because each day is shorter. This means that seasonal cycles are divided into more frequent sunrises and sunsets. The planet experiences the same journey around the sun, but it marks that journey with a greater number of light and dark intervals. If you were somehow able to keep track, you would notice that the stars return to the same position in the sky after more daily cycles than they do today. The rhythm of the cosmos feels busier, more packed with transitions, even though the grand movement of the planet around the sun remains steady and unhurried. The sky itself responds to these patterns. During longer periods of daylight in a given region, the atmosphere warms, air rises, clouds form, storms become more likely. During periods of extended darkness, the air cools, clouds thin, the surface loses heat back into space. These cycles influence where water collects and where it disappears. In some regions, seasonal rains carve temporary channels across the land, filling shallow basins that become brief, shimmering lakes. In others, long dry spells leave the ground cracked and dusty, waiting for the next shift in the planet's path around the sun. Life follows these changes closely. Microbial communities in shallow waters expand and contract with the availability of sunlight and nutrients. During bright, warm periods, photosynthetic microbes become more active, producing oxygen and building up layers in stromatolites. During darker, cooler times, other types of microbes take over, feeding on stored organic material or using chemical reactions to sustain themselves. These seasonal patterns create a kind of slow, breathing motion in the living world. Growth and retreat, expansion and pause. A rhythm tied not to clocks or calendars, but to the turning of the planet and the steady presence of the sun. The longer-term changes in Earth's rotation also have subtle effects on the planet's internal systems. The faster spin of the early Earth influences the movement of air and water, shaping wind patterns and ocean currents. Stronger rotation can lead to more pronounced circulation patterns, which in turn affect how heat and chemicals are distributed around the globe. These patterns help connect distant regions. A chemical released by a volcano in one part of the world can eventually influence ocean chemistry in another. Heat absorbed in the tropics can be carried toward cooler regions by moving water and air. The planet becomes a network of linked systems, all responding in one way or another to the turning of the Earth beneath the sun. The moon's influence remains ever present, Its gravitational pull not only shapes the tides, but also stabilizes the tilt of Earth's axis. This stability helps keep the seasons within a relatively predictable range. Without the Moon, the planet's tilt could vary wildly over time, leading to extreme and chaotic shifts in climate. In Kenorland's era, this stabilizing effect is already at work, quietly guiding the long-term pattern of sunlight across the surface. The result is a world that, despite its harshness and simplicity, maintains a kind of balance that allows life to persist and slowly evolve. Night in this ancient world carries a different feeling as well. With fewer gases and particles in the air to scatter light, the stars shine with remarkable clarity. The Milky Way stretches across the sky as a bright textured band. The moon casts strong, pale light across the land, creating sharp contrast between illuminated rock and deep shadow. The shorter nights pass quickly, but they are no less important. During these hours of darkness, the surface cools, chemical reactions slow. Some microbes shift their metabolic processes, taking advantage of the absence of sunlight to carry out different forms of energy production. This daily alternation between light and dark becomes a fundamental driver of biological rhythms, even in this early, microscopic world. The idea of an internal clock, so familiar in humans and animals, has its roots in these ancient cycles of day and night. Over immense stretches of time, the gradual slowing of Earth's rotation continues. The days grow longer by tiny increments, too small to notice in any single lifetime, but significant across hundreds of millions of years. The moon drifts farther away. The tides slowly lose some of their height. The rhythm of the planet's spin eases into a more measured pace. Kenorland exists in the middle of this long transition, a world caught between the faster days of Earth's youth and the longer days of its future. The interplay between sunlight, seasons, and rotation also influences the planet's climate on larger scales. Changes in how much light different regions receive can affect where ice forms and where it melts. This, in turn, alters how much sunlight the planet reflects back into space, creating feedback loops that can amplify warming or cooling trends. During periods when large areas of the surface become covered in ice, the planet reflects more sunlight, which can lead to further cooling. When ice retreats, darker rock and water absorb more heat, promoting warming. These processes can help drive the planet into and out of extended glacial periods. All of this unfolds slowly, guided by the steady motion of Earth around the Sun and the even steadier influence of the Moon. From the perspective of standing on Kenorland's surface, these grand cycles are not immediately visible. What you notice instead are the simpler, more immediate changes. The angle of the sun as it rises and sets, the warmth of the rock under your hand during the day, the chill that settles in after nightfall, the occasional shift in weather that brings rain or clears the sky. These small, everyday experiences are the surface expression of a much larger system, one that ties together the motion of celestial bodies, the chemistry of the atmosphere, the flow of water, and the activity of life. At the boundary where water meets stone, where the ancient sea laps quietly against the bare surface of Kenorland, something small and easily overlooked is shaping the entire future of the planet. There are no animals here, no plants reaching for the sky, no movement that catches the eye from a distance, and yet this narrow zone along the shoreline is one of the most active places on Earth, not because of crashing waves or shifting land, but because of life that exists at a scale too small to see. Let's ease ourselves down toward that edge, not with the expectation of finding anything dramatic, but with the patience to notice what usually goes unnoticed. The surface of the rock near the waterline is damp and darkened. Thin films cling to it, almost like a stain left behind by the tide. If you look closer, those films resolve into layered structures, soft in places, firmer in others, shaped by countless tiny organisms living together in a tightly woven community. These are microbial mats, and in the time of Kenorland, they are among the most complex ecosystems the planet has to offer. Each mat is made up of billions of individual cells, most of them bacteria and archaea, arranged in layers that reflect how they interact with their environment. The top layer is usually home to microbes that rely on sunlight. They spread themselves out to catch as much light as possible, using it to drive chemical reactions that provide them with energy. Beneath them live organisms that prefer dimmer conditions, feeding on the byproducts of the upper layers. Deeper still are microbes that thrive without oxygen at all, using sulfur, iron, or other chemicals to sustain themselves. This layered structure turns a simple patch of wet rock into a miniature world, complete with its own internal cycles of energy and matter. If you were to carefully lift a piece of one of these mats, you would notice that it feels slightly spongy, almost like a living fabric. Sediment sticks to its surface, trapped by the sticky substances the microbes produce. Over time, this sediment builds up, forming thin layers that the mat grows through and over. As this process repeats, the structure slowly rises from the seafloor or rock surface, creating rounded shapes that can reach up into the shallow water. These formations, known as stromatolites, are some of the oldest visible signs of life on Earth. They're not just biological features, they're geological ones as well, because their growth leaves a physical record in the stone that can survive for billions of years. In Kenorland's time, stromatolites are common along warm, shallow coastlines. The conditions there are ideal. Sunlight penetrates easily. Nutrients wash in from the land. The water is shallow enough to warm during the day and cool at night, creating gentle cycles that the microbes can adapt to. The tides play an important role in this environment. As the water rises and falls, it alternately covers and exposes the mats. When exposed, the upper layers are bathed in air and sunlight. When submerged, they interact with the chemistry of the sea. This constant switching between conditions encourages a wide variety of metabolic strategies within a very small space. Some of the microbes in these mats perform a process that will eventually transform the entire planet. They use sunlight to split water molecules, releasing oxygen into their surroundings. This is oxygenic photosynthesis, and while it feels ordinary to you now, in this ancient world, it is something entirely new. The oxygen released by these microbes does not stay in one place for long. It dissolves into the water, it reacts with metals and minerals, it escapes into the air. Each tiny puff of gas is a small step in a much larger transformation. At first, this oxygen mostly disappears into chemical reactions. Iron in the water reacts with it, forming solid particles that sink to the bottom. Sulfur compounds in the rocks and sediments absorb it as well. The environment around the mats becomes a place of constant chemical change, with oxygen appearing and vanishing as quickly as it is produced. This makes the immediate surroundings of a microbial mat a patchwork of conditions. Some spots are rich in oxygen, others are completely devoid of it. Microbes that thrive in one zone might die in another.
The result is a finely tuned community where different organisms occupy very specific niches, each adapted to a narrow range of chemical and physical conditions. This is what an ecosystem looks like at the edge of simplicity. There are no predators or prey in the familiar sense. There are no food chains you can easily draw on a diagram. Instead, there are networks of chemical exchange. One organism's waste becomes another's resource. Energy flows through the system in the form of electrons passed from one molecule to another, guided by the chemistry of the environment. The ocean just beyond these mats plays its own part in the system. Waves and currents bring in fresh water and dissolve materials from farther out to sea. Rivers carry minerals from the land. Volcanic activity adds new elements from below. The mat becomes a meeting point for all of these influences, a place where the planet's different layers come together. Life in the deeper ocean follows a different pattern. Far below the reach of sunlight, in water that remains dark and cold, microbes rely on chemical energy rather than light. Some of them live near hydrothermal vents, where hot, mineral-rich fluids rise from the seafloor. These fluids carry compounds like hydrogen sulfide and methane, which can be used as fuel for life. Around these vents, small ecosystems form. built entirely on chemistry rather than sunlight.
Microbes grow in thick clusters on the rocks, forming the base of a food web that, in later eras, will include larger, more complex organisms. In Kenorland's time, the system remains simple, but it is no less important. It shows that life can find a way to exist in places that seem, at first glance, completely inhospitable. The land itself also hosts microbial life, though in more limited and fragile forms. Thin films of bacteria and archaea spread across damp surfaces after rain. They cling to the edges of temporary pools and shallow channels. When the water dries up, many of these organisms enter dormant states, waiting for the next chance to become active again. These land-based communities are pioneers. They are among the first living things to explore the surface of the continent. Their presence, small as it is, begins to change the way the land interacts with the air and water. They trap dust. They alter the chemistry of rainwater that passes over them. They contribute in tiny increments to the breakdown of rock and the formation of early soil-like material. The impact of microbial life extends far beyond the places where it physically lives. The oxygen released by photosynthetic microbes eventually begins to accumulate in the atmosphere. This changes the chemistry of the sky. It leads to the formation of an ozone layer that shields the surface from harmful ultraviolet radiation. It makes new forms of energy production possible for organisms that can use oxygen in their metabolism. These changes do not happen quickly. They unfold over hundreds of millions of years. But they all trace their origin back to these simple, layered communities at the edge of land and sea. The presence of oxygen also changes the ocean itself. As iron is removed from the water and locked away in sediments, the sea becomes clearer. Light can penetrate deeper. Photosynthetic microbes can expand into new regions. This creates a feedback loop where more life leads to more oxygen, which leads to conditions that support even more life. At the same time, this new gas creates challenges. Oxygen is highly reactive. It damages the internal chemistry of organisms that are not adapted to it. Many microbes that once thrived in oxygen-free conditions find themselves pushed into deeper waters or isolated pockets where the gas cannot reach. Others evolve ways to cope with or even use oxygen, opening up new metabolic pathways. This period becomes one of both opportunity and loss, of expansion and extinction happening side by side. If you could watch this process from above, it would not look like a dramatic struggle. There would be no visible battles or sudden changes. The surface of the sea would still rise and fall with the tide. The sun would still move across the sky.
But at the microscopic level, entire worlds would be forming and dissolving, reshaped by shifts in chemistry that play out over timescales far longer than any single organism can experience. The simplicity of these ecosystems is part of what makes them so powerful. Without complex bodies or specialized organs, microbes can adapt quickly. They can exchange genetic material. They can experiment with new ways of using the resources around them. This flexibility allows them to respond to changes in the environment that would wipe out more specialized forms of life. In this sense, the earliest ecosystems are not fragile. They are resilient. They persist through climate swings, volcanic eruptions, changes in ocean chemistry, and shifts in the atmosphere. They bend and adjust rather than break. The role of these microbial communities in shaping the planet cannot be overstated. They are not just living on the Earth. They are helping to build it, layer by layer, gas by gas, mineral by mineral. Even the rocks beneath your feet in the modern world carry the marks of their work. The oxygen in the air, the iron in your tools, the very structure of the continents all carry a trace of the processes that began in these simple ancient mats. The edge of simplicity is also the edge of possibility. As the supercontinent continues to shift and the environment grows more varied, these microbial pioneers will encounter new habitats. Newly formed coastlines will offer fresh surfaces to colonize.
Shallow seas will expand and contract. Chemical gradients will appear in places they did not exist before. Each new environment becomes another opportunity for life to explore, to adapt, and to leave its mark. The story of complexity, of plants, animals, and ecosystems you would recognize, does not begin with a sudden leap. It begins here, with these quiet, layered communities spread thinly across a world of stone and water. The future of the planet is being prepared in places that are easy to miss, in thin films on rock, in shallow pools warmed by the sun, in dark waters near the seafloor where heat and chemistry meet. Something subtle begins to change in the world, not with a sound or a sudden movement, but with a quiet chemical whisper that spreads through water, stone, and sky. There is no moment you can point to and say, "Here, this is when it happened." Instead, the shift unfolds like a slow dawn that takes hundreds of millions of years to fully brighten. The planet, in its own patient way, starts to react to a new presence in its environment, a gas that until now has been little more than a trace. This is the time when Earth begins to learn how to rust. If you stand at the edge of one of Kenorland's shallow seas during this era, the scene looks much like it always has. The tide moves in and out. The surface of the water reflects the hazy light of the sun. The shoreline is lined with dark rock and thin films of microbial life. Nothing in the wide view suggests that a transformation of planetary scale is underway. But in the water itself, and in the air just above it, chemistry is beginning to tell a different story. Oxygen, once produced and quickly hidden away by reactions with rock and metal, is starting to linger. The planet's vast chemical sponge, which for so long absorbed every molecule of this new gas, is slowly reaching its limit. The iron in the oceans has reacted. The sulfur in the rocks has bound what it can. The easy hiding places for oxygen are filling up. So now, for the first time in Earth's history, small amounts of this reactive gas remain free, drifting in the water, escaping into the atmosphere and changing the rules of how the world works. This process is known as the Great Oxygen Shift, or more formally, the Great Oxidation Event. But from the perspective of standing in this ancient world, it feels less like an event and more like a gradual realization, as if the planet is slowly becoming aware of a new ingredient in its own system. The first place this change makes itself known is in the oceans. For hundreds of millions of years, iron has been dissolved in seawater, carried there by rivers, volcanic activity, and chemical weathering of the land. In water without oxygen, iron stays in solution, invisible and quietly mixed into every wave and current. But when oxygen appears, even in small amounts, iron reacts. The reaction is simple, but powerful. Iron and oxygen combine to form iron oxide, a solid, rust-like material that can no longer stay dissolved in the water. Tiny particles begin to form, clumping together and slowly sinking toward the seafloor. If you could watch this process in slow motion, you might see faint cloudy trails in the water, drifting downward like underwater snow. Over time, these particles settle into thin layers of sediment, spreading across the ocean floor in wide, flat sheets. This is how the planet begins to record its own transformation. Layer after layer, iron-rich sediments build up, alternating with layers of other materials like silica and carbonate. The result is a striking pattern preserved in rock, known today as banded iron formations. Each band represents a moment in deep time when oxygen levels rose just enough to trigger widespread rusting in the sea. These formations can be found billions of years later in places like Australia, South Africa, and North America, standing as quiet monuments to a world learning how to breathe in a new way. But the oceans are only part of the story. As oxygen starts to escape into the air, the atmosphere begins to change as well. Methane, which has been one of the most important greenhouse gases keeping the planet warm, reacts readily with oxygen. When the two meet, they form carbon dioxide and water, reducing the amount of methane in the sky. This shift alters how the planet holds onto heat. With less methane to trap warmth, the atmosphere becomes less efficient at keeping the surface warm. Over long periods, this cooling effect can become significant, especially when combined with changes in cloud cover and the reflectivity of ice. The result may be some of the coldest climates the Earth has ever experienced. During certain stretches of this era, ice may spread far beyond the poles, covering large portions of the land and sea. Glaciers creep across the bare surface of Kenorland, grinding rock into fine powder.
Sea ice forms over wide areas of the ocean, reflecting sunlight back into space and reinforcing the cooling trend. From the surface, this frozen world feels stark and quiet, even more so than before. The sound of moving water is replaced by the slow creak and crack of ice. The wind carries a sharper chill. The sky, clearer of greenhouse haze, appears brighter and more open, with stars shining through cold, thin air. Yet even in these conditions, life does not vanish. Beneath the ice, in pockets of liquid water warmed by geothermal heat or insulated by thick layers of snow and ice, microbial communities persist. Along volcanic regions, warm springs and vents provide refuges where chemical energy continues to flow. Life retreats, adapts, and waits for the climate to ease. The oxygen that triggers this cooling is, at the same time, opening doors to entirely new ways of living. For organisms that evolve the ability to use oxygen in their metabolism, a powerful new energy source becomes available. Oxygen-based respiration allows cells to extract far more energy from the same amount of organic material than older oxygen-free pathways. This surplus of energy can support larger cells, more complex internal structures, and eventually entirely new forms of life. But in this early stage, oxygen is still a dangerous guest. Many of the organisms that dominate the planet during this time evolved in a world without it.
Their internal chemistry is not equipped to handle such a reactive substance. Oxygen damages proteins, disrupts membranes, and interferes with vital chemical processes. For these life forms, the rise of oxygen is not a gift, it is a threat. Entire microbial communities may be pushed into deeper waters, buried beneath sediments, or driven into isolated environments where oxygen cannot easily reach. Some adapt by developing protective mechanisms or new metabolic strategies. Others disappear from the surface of the planet, surviving only in hidden niches where ancient conditions persist. This is one of the first major mass extinctions in Earth's history, though it looks nothing like the dramatic events that will one day wipe out dinosaurs or reshape forests. There are no visible signs of catastrophe, no empty landscapes or sudden changes in the scenery. The drama plays out at the level of chemistry and cells, in the invisible world of microbes. The land also begins to respond to the presence of oxygen. Rocks exposed to the air start to change colour. Minerals that were once stable in an oxygen-poor environment begin to oxidize. Iron-bearing rocks take on reddish and brownish tones as rust forms on their surfaces. Over time, entire regions of the continent develop these colours, a visible sign that the chemistry of the atmosphere has shifted. Rainwater, now carrying dissolved oxygen, becomes a more effective agent of chemical weathering. It reacts more readily with minerals in the rock, breaking them down and carrying their components into rivers and the sea. This increases the flow of nutrients into coastal waters, which can encourage the growth of microbial communities. In this way, the oxygen shift creates feedback loops that tie together land, sea, air, and life. More oxygen leads to more weathering. More weathering leads to more nutrients in the ocean. More nutrients support more photosynthetic microbes. More microbes produce more oxygen. The system becomes self-reinforcing, pushing the planet further along its new chemical path. High above the surface, another important change begins to take shape. As oxygen accumulates in the upper atmosphere, sunlight breaks some of its molecules apart. The freed oxygen atoms recombine in a different form, creating ozone. This thin layer of ozone absorbs much of the sun's harmful ultraviolet radiation, which previously reached the surface unchecked. This new shield does not appear overnight. It builds slowly, molecule by molecule, but over time, it begins to make the surface of the planet a safer place for life. With less damaging radiation reaching the ground, the potential for organisms to survive outside of water increases. The land, once an environment too harsh for most life to tolerate, becomes slightly more welcoming. Thin microbial films can persist longer on exposed surfaces. Shallow pools become less hostile.
The idea of life on land, which now seems impossible, starts to move into the realm of possibility. The sky itself looks different as the atmosphere changes. The scattering of sunlight shifts, and the color of daylight gradually moves closer to the blue you recognize. The air becomes clearer in some regions, less hazy with methane and other gases. The balance of clouds and rainfall adjusts as the chemistry of the atmosphere evolves. These changes do not happen evenly across the planet. Some regions see more oxygen than others. Coastal areas near active microbial mats experience higher levels first. Inland regions lag behind. High altitudes and low altitudes respond differently. The atmosphere becomes a patchwork of conditions, with pockets of higher and lower oxygen content. This unevenness adds another layer of complexity to the world. Microbial communities respond by spreading into new areas where conditions allow. In some places, oxygen-loving organisms gain an advantage. In others, oxygen-sensitive life holds on longer. The result is a shifting mosaic of ecosystems, each shaped by local chemistry, geography, and climate. The oceans reflect this patchwork as well. Surface waters near productive coastlines become more oxygen-rich. Deeper waters remain dark and oxygen-poor. This creates strong chemical gradients that influence how nutrients and metals move through the sea. Some areas become hotspots of biological activity. Others remain relatively quiet and unchanged.
Over time, these differences can influence the circulation of the ocean itself. Oxygenated water is often cooler and denser, which can cause it to sink and move along the seafloor. This movement helps distribute oxygen and nutrients into deeper regions, slowly expanding the reach of the new chemistry. The transformation of the planet is not driven by a single cause or a single place. It is the result of countless small interactions happening everywhere at once. Sunlight strikes microbial mats. Microbes release oxygen. Oxygen reacts with iron. Iron settles into rock. Gases shift in the sky. Climate cools and warms. Ice advances and retreats. Life adapts or disappears. From a human perspective, this might sound like a dramatic sequence of events. But from the planet's point of view, it is simply another phase in a long, continuous process of change. If you stand quietly in this imagined world and let time pass, the changes are almost impossible to see. The sea still moves, the wind still blows, the land still sits under the sky. Yet, beneath that apparent stillness, the chemistry of everything is slowly being rewritten. One of the most remarkable aspects of this shift is how deeply it connects the smallest and largest scales of the planet. Tiny cells, invisible to the naked eye, alter the composition of the atmosphere. That atmospheric change influences global climate. Climate shifts reshape the distribution of ice and water. Those changes affect how continents erode and how oceans circulate, and all of it feeds back into the conditions that shape life itself. The planet becomes a single, interconnected system, with oxygen acting as one of its most powerful linking threads. As Kenorland continues to strain and fracture, the movement of the land adds another layer to this story. New coastlines form, exposing fresh rock to weathering. Rivers carry newly released minerals into the sea. Shallow seas expand in some regions, providing more space for microbial mats to grow. Each new stretch of coastline becomes another site where oxygen can be produced, released, and spread. The great landmass, once a single, continuous body, begins to break into pieces, and in doing so, it multiplies the places where life and chemistry can interact. The world becomes more varied, more complex, and more dynamic. The rise of oxygen is not just a change in the air, it is a change in what the planet can be. With this new gas, the Earth steps onto a different path, one that leads toward greater biological complexity, toward ecosystems that will one day include plants, animals, and eventually minds capable of looking back and trying to understand how it all began. But for now, the world is still in the middle of its first great chemical awakening. The rusting of iron in the sea, the reddening of rocks on land, the clearing of the sky, and the cooling of the climate are all parts of the same slow transformation. The planet is learning how to live with oxygen, and in the process it is becoming a very different place from the one it used to be. Cold arrives in this ancient world not as a sudden shock, but as a quiet, steady presence that slowly claims more and more of the horizon. The sun still rises, light still touches the land and the sea, yet something in the balance between warmth and space has shifted, and the planet begins to hold on to less of the heat it once kept so easily. Kenorland, already a place of bare stone and wide skies, starts to feel the long reach of ice. Picture standing near the edge of the great supercontinent, looking out across a landscape that seems to stretch forever. The air carries a sharper bite now, even during the brighter parts of the day. The wind feels cleaner, thinner, as if something heavy has been lifted from the atmosphere. This is one of the subtle effects of the changing sky. With methane levels falling and oxygen becoming more common, the blanket of greenhouse gases that once trapped warmth around the planet has begun to thin. Heat escapes more easily into space. The process is slow, drawn out over millions of years, but its effects gradually become impossible to ignore. Regions that were once cool become cold. Cold regions grow colder still. Snow begins to linger longer in places where it once melted away each season. Glaciers, small at first, start to form in high latitudes and at higher elevations, their bright surfaces reflecting sunlight back into the sky. That reflection matters. Ice is far more reflective than dark rock or open water.
When sunlight hits a glacier or a frozen sea, much of that energy is bounced back into space instead of being absorbed by the planet. This creates a feedback loop. More ice leads to more reflection. More reflection leads to less heat being absorbed. Less heat allows more ice to form. The world begins to cool itself further, simply by becoming brighter. Under the ancient sun, which already provides slightly less energy than the one you know, this effect can be powerful. Over long stretches of time, ice spreads outward from the poles, creeping toward lower latitudes. In some periods, it may reach far into regions that would one day be warm and temperate. The image of a mostly frozen Earth, sometimes called a Snowball Earth, is one of the most striking ideas in planetary science. While the exact extent of these ice ages during Kenorland's era is still a topic of careful study, there is strong evidence that the planet experienced episodes of widespread glaciation that reshape both land and sea. From the surface, these changes transform the world. Glaciers move slowly, almost imperceptibly, but their impact is immense. As they advance, they grind the rock beneath them into fine powder. They scrape away surface layers, carve shallow valleys, and leave behind long, smooth grooves in the stone. The land that emerges after the ice retreats looks different from what came before, reshaped by pressure and motion rather than by wind and water alone.
Standing near the edge of a glacier, you might hear the faint, deep creaking of ice under its own weight. The sound is low and distant, like the planet itself shifting in its sleep. Fractures form, blocks of ice break away, meltwater trickles along the base, carving small channels that carry freshly ground sediment toward the sea. The oceans respond to the cold in their own way. Sea ice forms over large areas, especially in higher latitudes. In some periods, ice may cover much of the surface, leaving only narrow bands of open water near the equator or in regions warmed by volcanic activity. Beneath this frozen lid, the ocean remains liquid, insulated by the ice above, and warmed by heat rising from the planet's interior. Life retreats into these hidden spaces. Microbial communities persist beneath the ice, clinging to the undersides of frozen surfaces or gathering near hydrothermal vents on the seafloor. These vents, fueled by volcanic heat, create pockets of warmth and chemical energy in an otherwise cold, dark world. Around them, life continues its slow, patient work, largely untouched by the changes happening at the surface. In shallow coastal areas, ice forms and melts with the seasons, scraping across microbial mats and reshaping the edges of the land. Some communities are destroyed, others re-establish themselves when conditions allow. This constant disturbance creates a cycle of loss and renewal, pushing life to adapt to increasingly challenging environments. The sky above these frozen landscapes looks different as well. With fewer greenhouse gases and less moisture in the air, the atmosphere becomes clearer. Sunlight travels through it with less scattering, creating sharper contrasts between light and shadow. The blue of the sky deepens in some regions. Clouds become thinner or more seasonal, forming where temperature differences and moisture allow. Storms still occur, but their character changes. Snow becomes more common than rain in colder areas. Winds sweep in across wide ice fields, pick up fine, powdered snow, and carry it in low, drifting sheets that skim over the surface of the land. The sun, when it rises, glints off the ice, creating fields of brightness that can be almost blinding. Even in this ancient world, light and reflection combine to create moments of stark, quiet beauty. Despite the cold, volcanic activity continues. In some regions, heat from below keeps the land free of ice. Lava flows cut through frozen terrain, sending steam and gas into the air as they meet snow and ice. Hot springs form around cracks in the crust, creating small oases of liquid water surrounded by frozen ground. These places become refuges for life, gathering points where microbes can survive and spread when conditions elsewhere become too harsh. The contrast between fire and ice becomes one of the defining features of the planet during these times. Frozen horizons sit alongside glowing rock. Snow-covered plains are interrupted by dark, steaming fissures in the ground. The surface of the world becomes a patchwork of extremes, shaped by forces that come from both above and below. The presence of ice also changes how the land interacts with the sea. When large amounts of water are locked away in glaciers and ice sheets, sea levels drop. Coastlines shift outward. Shallow seas retreat, exposing new stretches of land that were once underwater. Rivers cut deeper channels as they flow across the newly revealed terrain, carrying sediments and minerals into the ocean basins. When the climate eventually warms and ice begins to melt, the process reverses. Water returns to the seas, sea levels rise, coastlines move inland, low-lying areas flood, creating new shallow marine environments that can be quickly colonized by microbial life. These cycles of freezing and thawing reshape the edges of the supercontinent again and again, creating a constantly changing boundary between land and water. The chemistry of the ocean shifts during these periods as well. Cold water holds more dissolved gases, including oxygen. As surface waters cool and sink, they can carry oxygen into deeper parts of the ocean, altering conditions far below the ice. This can open up new habitats for organisms that rely on oxygen, while changing the availability of chemicals used by those that do not.
At the same time, the grinding action of glaciers produces fine sediment that is washed into the sea when the ice melts. This sediment carries minerals that can feed microbial growth in coastal waters, creating bursts of biological activity after long, cold intervals. The climate, the chemistry of the sea, and the activity of life become tightly linked in these cycles. Each influences the others, creating patterns that play out over tens of millions of years. The ancient sun remains a constant presence throughout all of this. Its light still drives photosynthesis in the shallow waters that remain free of ice. Its energy still warms the surface during the day. Its path across the sky still defines the rhythm of light and darkness. But the way the planet responds to that light is different now, filtered through a colder atmosphere and reflected by a brighter, more frozen surface. Even the length of the day and the pull of the moon continue to shape these icy periods. Stronger tides driven by the closer moon can help break up sea ice near coastlines, exposing patches of water to sunlight and air. This creates narrow zones where microbial life can persist and oxygen can continue to be produced, even during colder phases. These small openings may play an important role in keeping the planet from becoming completely locked in ice. The tilt of the Earth's axis also influences where ice forms and how far it spreads.
Regions that receive less sunlight for long periods become centres of glaciation. Areas closer to the equator, bathed in more consistent light, act as refuges where open water and active ecosystems can survive. Over time, changes in volcanic activity, the buildup of greenhouse gases, and shifts in the planet's orbit and rotation can tip the balance back toward warming. When that happens, the ice begins to retreat. The process is not gentle. As glaciers melt, vast amounts of water are released into rivers and seas. Floods reshape the land. Sediment is carried far from its original source. The ocean receives a surge of fresh water and minerals which can change its circulation and chemistry. Microbial communities respond quickly. New coastlines and shallow seas provide fresh surfaces to colonize. Nutrient-rich waters encourage growth. Oxygen production increases, reinforcing the atmospheric changes that helped bring about the warming in the first place. The planet, in this way, moves through cycles of cold and warmth, driven by a combination of geological, chemical, and biological processes. None of these systems operates alone. Each is part of a larger network that links the deep interior of the Earth to the sky above it. From a human perspective, these ice ages might seem like distant, abstract events. But in the context of Kenorland's story, they are central chapters in the planet's learning process. They test the resilience of life. They reshape the land. They alter the chemistry of the oceans and the air. They also prepare the world for what comes next. The breaking apart of the supercontinent accelerates during and after these periods of glaciation. Ice and water exploit weaknesses in the crust. The weight of glaciers and the release of that weight when they melt can influence how the land rises and falls. Rifts widen. New ocean basins deepen. Each cycle leaves the planet a little more divided, a little more complex. Standing at the edge of this frozen horizon, it is easy to think of the world as harsh and unwelcoming. Yet, even in the coldest stretches of its history, the Earth remains alive. Life persists in dark water beneath ice, in warm pockets near volcanic heat, in thin films on rock that thaw briefly under the sun. The ice ages of Kenorland are not just times of survival, they are times of transformation. The conditions they create push life to explore new strategies, to adapt to extremes, and to take advantage of the opportunities that appear when the world warms again. The chemistry of the atmosphere and ocean continues to shift. The shape of the land continues to change. Far from the icy coastlines and the quiet work of microbial mats, a different kind of change is unfolding deep within the body of the planet. It does not announce itself with a single dramatic moment. There is no clear line between a world that is whole and a world that is beginning to come apart. Instead, the transformation starts as a subtle tension, a slow stretching of stone that takes place over spans of time so long they blur the idea of before and after. Kenorland, once a vast and continuous landmass, is beginning to feel the strain of the forces beneath it. The crust that holds this ancient world together is not a single, solid shell. It is broken into enormous plates, each one riding atop the hotter, softer mantle below. The mantle itself is in constant motion, stirred by heat rising from the planet's deep interior. This movement is slow and steady, like the turning of thick liquid, but its influence is relentless. It pushes, pulls, and nudges the plates above, guiding them into patterns of collision separation, and sliding that reshape the surface over millions of years. For a long time, these motions helped bring Kenorland together. Ancient cratons drifted toward one another and fused, building the backbone of the supercontinent. Now that same restless movement begins to work in the opposite direction. In some regions, the mantle pushes upward more strongly, thinning the crust from below. The rock above stretches just slightly at first. Tiny fractures appear, so small they might go unnoticed even if you were standing directly on them. These are not dramatic chasms or yawning gaps. They are hairline cracks, narrow lines in the stone that mark places where the land is beginning to give way. Over time, as heat continues to rise and pressure continues to build, these fractures grow. They widen into long, shallow valleys that can extend for hundreds of kilometers. The ground on either side tilts gently downward toward the center of these rifts, creating broad, low basins that collect water and sediment. If you were to walk across one of these early rift zones, you might notice that the land feels different beneath your feet. The rock is more broken, more uneven. Warmth seeps up from below, faint but persistent. In some places, small vents release wisps of gas into the air, carrying the sharp scent of sulfur and other volcanic compounds. These rifts are not just surface features, they are windows into the deep interior of the planet. As the crust thins, molten rock from the mantle can rise closer to the surface. Sometimes it breaks through entirely, spilling out as lava that spreads across the floor of the rift and cools into new crust. Each of these eruptions adds another layer of stone to the growing valley, even as the land on either side continues to pull apart. This process creates a strange kind of balance. The supercontinent is breaking, but at the same time it is being rebuilt from below. New rock forms where old rock is stretched and thinned, creating a patchwork of ancient and freshly solidified stone across the surface. Water plays an important role in shaping these regions as well. Rain falling into rift valleys collects in long, narrow lakes. Rivers flow along the low points, carrying minerals from the surrounding highlands into these basins. Over time, thick layers of sediment build up, burying older rock and creating a geological record of the slow separation taking place. In some areas, these rift valleys dip low enough to connect with the sea. When that happens, seawater floods in, creating long, shallow arms of the ocean that reach deep into the heart of the continent. These new coastlines become active zones of life and chemistry, much like the original edges of Kenorland, but now spread across the interior. The appearance of these inland seas changes the climate locally. Water moderates temperature, softening the extremes between day and night. Moisture in the air increases. Clouds form more readily. Rain falls more often along the shores of these young basins. The land around them becomes a little less stark, a little more dynamic, shaped not just by wind and stone, but by the steady presence of water. Microbial life follows these changes closely. New shorelines provide fresh surfaces to colonize. Shallow waters offer ideal conditions for stromatolites and microbial mats to spread. The oxygen produced in these areas adds to the growing presence of the gas in the atmosphere, reinforcing the chemical shifts already underway. The breaking of the supercontinent in this way multiplies the places where life and the planet interact most strongly. As rifts widen and deepen, the process can reach a tipping point. The crust becomes so thin that it can no longer support itself. Large sections sink, seawater rushes in. What was once a valley becomes a narrow ocean basin. This is how a supercontinent begins to turn into separate continents. From above, the change would look like a thin, winding line of water cutting across a vast landmass. Over millions of years, that line widens into a sea. The sea grows into an ocean. The land on either side drifts farther apart, carried by the slow movement of the plates beneath them. The scale of this transformation is difficult to fully imagine. The opening of an ocean can take tens of millions of years. A distance that might feel like a short drive to you can represent a journey of hundreds of millions of years for the land itself. The forces driving this separation are not uniform across the planet. Some regions of Kenorland remain stable for long periods, held together by thick ancient crust that resists stretching. Other regions break more readily, becoming centres of rifting and volcanic activity. This unevenness gives rise to a complex pattern of cracks, basins, and rising and falling blocks of land. The surface becomes more varied, more textured, as flat plains give way to valleys, ridges, and shallow seas. Earthquakes become more common in these active zones. As plates move and crust stretches, stress builds up in the rock. When that stress is released, the ground shifts suddenly. The motion can be gentle or violent, but either way, it leaves its mark. New fractures form, old ones widen. Sediment slumps into low areas. The landscape is subtly rearranged with each event. Volcanoes often accompany this activity. Where the crust is thin, magma can find easy paths to the surface. Long cracks in the ground become lines of fire, releasing lava that flows outward and cools into fresh stone. These eruptions can reshape entire regions, covering older features and creating new ones in their place. The gases released during these events continue to influence the atmosphere. Carbon dioxide and water vapour add to the greenhouse effect. Sulfur compounds can lead to short-term cooling by reflecting sunlight. The balance between these influences contributes to the long-term climate patterns that play out across the planet. The ocean floor is also changing during this time. As new basins open, fresh crust forms along their centres. This new seafloor is hot and buoyant at first, sitting higher than older, cooler crust. Over time, it cools, becomes denser, and sinks lower. This process helps shape the depth and contours of the growing oceans. Water circulating through cracks in the young seafloor becomes heated by the underlying rock. It rises back into the ocean, carrying dissolved minerals and chemicals. These hydrothermal systems create environments rich in energy, where microbial life can thrive even in the absence of sunlight. The breakup of Kenorland, then, is not just a mechanical process of land pulling apart. It is a chemical and biological one as well, creating new habitats and new pathways for energy and matter to move through the planet. As the land divides, the climate begins to change in more regional ways. Large continuous interiors give way to smaller land masses surrounded by water. This increases the influence of the ocean on weather patterns. Temperatures become more moderate near the coasts. Rainfall patterns shift. Winds find new paths around the edges of the continents. Regions that were once dry and extreme begin to experience more frequent moisture. New river systems form, draining into the expanding seas. These rivers carry minerals and nutrients from the land into the ocean, supporting the growth of microbial communities along the coasts. The atmosphere, already altered by rising oxygen, responds to these changes in circulation and moisture. Cloud patterns evolve, storm tracks shift. The distribution of heat across the planet becomes more complex, influenced by the growing network of oceans and seas. From a distance, the supercontinent still appears vast and dominant, but its unity is fading. Thin lines of water widen, shallow seas deepen, blocks of land drift slowly away from one another. The world becomes a mosaic of connected and separating pieces, each one following its own slow path across the surface of the planet. This process does not happen once and then stop. It unfolds in stages. Periods of relative stability are followed by bursts of activity. Rifts pause and then reopen. Oceans widen and then stabilize. The pattern of movement is irregular, shaped by the deep, complex flow of the mantle below. Through all of this, life continues its quiet work. Microbial mats spread along new coastlines. Oxygen production increases in shallow seas. Chemical gradients form in young ocean basins, creating diverse environments for different types of organisms. The breakup of the land creates a patchwork of habitats, each with its own conditions and challenges. This diversity becomes a driver of biological change. Isolated regions allow different microbial communities to evolve in slightly different ways. Over time, These differences can lead to new metabolic strategies and new forms of interaction between life and its environment. The separation of land also influences the movement of water and air on a global scale. As oceans open, currents begin to circulate around and between the new continents. These currents carry heat and nutrients across vast distances, linking distant regions of the planet in a slow, steady exchange. Winds respond to the changing shapes of a land and sea, shaping weather patterns that can persist for millions of years. The planet becomes more interconnected even as its surface becomes more divided. There is a certain quiet irony in this. The breaking of the world creates new ways for its parts to communicate. If you were to stand on a high ridge in this evolving landscape, you might look out over a view that includes both the old and the new. Ancient plains of solid rock stretch away in one direction, largely unchanged for hundreds of millions of years. In another direction, a long narrow sea glints in the sunlight, marking the path of a rift that is slowly becoming an ocean. The air carries the scent of salt near the water, and the faint trace of volcanic gases from active regions farther away. The ground beneath you feels solid, yet you know in this imagined moment that it is part of something in motion. The idea of a single, permanent supercontinent begins to lose its meaning here. Kenorland is no longer just a place. It is a phase in the planet's history, a stage in a long cycle of coming together and pulling apart that will repeat many times in the billions of years to come. The cracks forming in this ancient world are not signs of failure. They are part of how the planet renews itself. Old crust is broken down and recycled. New crust is formed. Chemical elements are redistributed. Life is given new spaces to explore. As the great landmass continues to separate, the world grows more complex, more varied, and more dynamic. The slow breaking of Earth's first giant landmass is not an ending. It is a turning point, a moment when the planet shifts from a world defined by unity to one defined by connection across distance. And as the pieces of Kenorland drift apart, they carry with them the foundations of the landscapes, climates, and living systems that will shape the deep future. Where land once stretched in a single, unbroken sweep across the face of the planet, water now begins to claim the low places, quietly and persistently, as if testing the shape of a new world. The gaps left behind by the slow separation of Kenorland do not remain empty for long. Gravity, rain, and the steady pull of the global ocean guide seawater into these widening basins, and with that movement, the planet enters another phase of its long story. The arrival of new oceans is not dramatic in the way a storm is dramatic. There is no single day when the world suddenly looks different. Instead, there is a gradual softening of the landscape. Valleys deepen, basins sink lower. Rivers that once flowed across dry land now end in shallow, expanding seas. Salt water creeps inland along the lowest paths, turning cracks in the crust into narrow channels, and those channels into long winding arms of the ocean. Standing at the edge of one of these young seas, you would see a shoreline that feels unfinished. The water is shallow and warm near the coast, often cloudy with sediment carried in by rivers. The land slopes gently into the sea rather than dropping off sharply. Wide tidal flats stretch out when the water retreats, leaving behind glistening surfaces of wet sand and mineral crusts that dry and crack under the sun. These places become centres of activity, not in the sense of movement you can easily see, but in the sense of interaction. Water meets rock, air meets sea, life meets both. The shape of the coastline itself changes constantly. During periods when ice melts and sea levels rise, water floods farther inland, drowning low-lying areas and creating new bays and inlets. When the climate cools and ice advances, sea levels drop, exposing more land and pushing the shoreline outward again. Over millions of years, this back-and-forth motion sculpts the edges of the continents, carving gentle slopes and leaving behind layers of sediment that record each advance and retreat. These young oceans are not just new bodies of water, they are new systems, with their own patterns of movement and chemistry. As seawater fills the basins formed by rifting, it comes into contact with fresh, newly formed crust on the ocean floor. This crust is hot and chemically active. Water seeps into cracks and pores in the rock, heats up, and reacts with the minerals it encounters. Then it rises back into the ocean, carrying dissolved elements like iron, sulfur, and silica. This circulation creates hydrothermal systems that can stretch for long distances along the centres of these young oceans. Around these underwater vents, warm, mineral-rich water mixes with the colder surrounding sea, creating gradients of temperature and chemistry that become ideal habitats for microbial life. In these dark, deep places, far from the reach of sunlight, life does not depend on the sun. Instead, it draws energy from chemical reactions, using the compounds released by the Earth itself. These communities are simple in structure, but they demonstrate something profound. Life on this planet is not tied to a single source of energy. It can take advantage of whatever pathways are available. Closer to the surface, the influence of the sun remains strong. Shallow coastal waters warm during the day and cool at night. Light penetrates easily, reaching the seafloor in many places. Here, microbial mats and stromatolites spread across new surfaces, building layered structures that rise slowly from the sediment. The oxygen they produce continues to alter the chemistry of the water and the air, reinforcing the changes that began during the Great Oxygen Shift. The opening of new oceans increases the total length of coastline on the planet. Instead of a single, continuous edge around a massive landmass, there are now many edges, many places where land and sea meet. Each of these boundaries becomes a site for weathering, erosion, and chemical exchange. Rain falling on land dissolves minerals from the rock and carries them into rivers. Those rivers flow into the sea, delivering nutrients and metals that feed microbial growth. The microbes release oxygen and other byproducts, which move back into the atmosphere and influence climate. The system becomes more interconnected, more layered, more responsive. Ocean currents begin to form in these new basins, driven by differences in temperature and salinity. Warm, less dense water near the surface flows toward cooler regions. Colder, denser water sinks and moves along the seafloor. These currents link distant parts of the planet, carrying heat, chemicals, and living organisms from one region to another. The movement of water also helps distribute oxygen into deeper parts of the ocean. As surface waters become oxygen-rich, some of that oxygen is carried downward by sinking currents, gradually expanding the zones where oxygen-dependent life can survive. This changes the structure of marine ecosystems. In earlier times, much of the deep ocean was a place dominated by chemical energy and low oxygen conditions. As oxygen begins to penetrate farther down, new metabolic pathways become possible. Some microbes adapt to take advantage of this new resource, while others retreat into places where oxygen remains scarce. The result is a growing diversity of environments, layered not just across the surface of the planet, but vertically through the water column as well. The land on either side of these new oceans also begins to change in response to the presence of nearby water. Regions that were once deep in the interior of a supercontinent now find themselves closer to the coast. Temperatures become more moderate. Moisture in the air increases. Clouds form more readily. Rain falls more often. Rivers become more stable, flowing year-round instead of only during brief wet periods. These changes soften the landscape. Chemical weathering becomes more effective in the presence of consistent moisture. Rocks break down more easily. Sediment is carried away and deposited in layers along the coast and on the ocean floor. Thin soils, still very different from the rich, organic layers of a future world with plants, begin to form in sheltered areas. Microbial life spreads across these damp surfaces, contributing organic material and helping to trap fine particles of sediment. The separation of the land also influences how air moves around the planet. Large continuous land masses create broad, simple wind patterns. As the continents break apart, the shape of the surface becomes more complex. Winds are redirected around coastlines, across narrow seas, and between drifting land masses. This leads to more varied weather patterns, with some regions becoming wetter and others drier. Storm systems begin to follow new paths. Seasonal cycles become more pronounced in some areas. The interaction between ocean and atmosphere grows richer, with heat and moisture constantly exchanged between the two. The climate, which once followed relatively simple global patterns, becomes more regional. Different parts of the planet begin to experience different conditions, shaped by their position relative to the new oceans, prevailing winds and currents. This regionalization has important effects on life. Microbial communities that once existed across wide, continuous environments now find themselves separated by water or by stretches of land that have become less hospitable. Isolation allows different populations to follow slightly different evolutionary paths, adapting to local conditions in ways that set them apart from their distant relatives. Over long periods, these small differences can accumulate, leading to new metabolic strategies, new chemical interactions, and greater biological diversity. The oceans themselves become highways for life. Microbes and other small organisms can be carried by currents across vast distances, spreading from one coastline to another. This movement helps mix genetic material between populations, linking distant ecosystems and allowing successful adaptations to spread. The deep sea plays its part as well. Water moving along the ocean floor carries chemical signatures from one region to another, influencing the conditions in places far removed from their source. The young oceans are not static basins. They continue to grow as the continents drift farther apart. New crust forms along their centres, pushing older crust outward. The basins deepen. The seafloor cools and sinks, creating space for more water. This growth influences sea level on a global scale. As the total volume of ocean basins increases, sea level can drop, exposing more land. When volcanic activity raises parts of the seafloor, or when large amounts of water are released from melting ice, sea level can rise again. These shifts add another layer of change to the shape of the coastlines and the distribution of shallow seas. Shallow seas are particularly important for life and chemistry. They are places where sunlight, nutrients, and living organisms come together. The bottom is often close enough to the surface for light to reach, allowing photosynthetic microbes to thrive. Sediments settle here, carrying minerals from the land. Chemical reactions occur at the interface between water and rock. These environments act as engines of oxygen production and nutrient cycling, feeding back into the atmosphere and the wider ocean. As the planet continues to evolve, the relationship between land and sea becomes more intricate. Rivers cut deeper channels across the continents, guided by the new slopes and basins created by rifting and subsidence. These rivers deliver water and sediment into the oceans in patterns that reflect the changing shape of the land. In some regions, deltas form where rivers meet the sea, creating broad, flat areas of sediment that extend the coastline outward. These deltas become additional zones of microbial activity, rich in nutrients and constantly reshaped by tides and currents. The sky above responds to all of this movement. Moisture from the oceans feeds clouds and storms. Heat released from the water influences wind patterns. The distribution of ice and open water affects how much sunlight is reflected or absorbed. The atmosphere becomes a dynamic partner in the evolving system, responding to changes below and influencing them in return. The planet at this stage begins to resemble something more like the Earth you know, not in appearance but in complexity. There are now multiple continents, separated by oceans that carry heat and life between them. There are regional climates instead of a single, dominant global pattern. There are varied environments instead of vast, uniform interiors. Yet the world is still simple in many ways. There are no forests to shape the land, no animals to move nutrients across the surface, no coral reefs to build massive structures in the sea. The primary architects of this world remain microbes and geological processes working together to create the conditions for what will come later. The opening of new oceans also has long-term consequences for the planet's deep interior. As crust is created and destroyed, chemical elements are cycled between the surface and the mantle. Water is carried down into the Earth at subduction zones, where old seafloor sinks back into the interior. This water influences how rocks melt and move deep below, affecting future volcanic activity and the movement of plates. The surface and the interior remain linked, each shaping the other in ways that play out over immense spans of time. If you were to stand on a high point overlooking one of these young oceans, you might see a world in transition. Behind you, ancient plains of rock and dust stretch away, remnants of the once unified supercontinent. Ahead of you, water glimmers in a long, narrow basin, reflecting the light of the sun and the muted colours of the sky. Along the shore, thin bands of darker material mark the presence of microbial life, quietly at work on the edge of land and sea. The air carries the faint scent of salt and minerals. The wind moves differently here, guided by the open space of the water and the uneven shapes of the land. It is a place that feels like a beginning. The separation of Kenorland does not erase the world that came before it. Instead, it builds upon it, taking the chemical, biological and geological foundations that were laid during the time of the supercontinent and rearranging them into new patterns. The planet becomes a patchwork of connected systems, each one influencing the others through the movement of water, air, rock, and life. As these new oceans widen and the continents continue their slow drift, the stage is set for further changes. The diversity of environments increases, the complexity of ecosystems grows, the interactions between land, sea, and sky become richer and more layered. The story of the planet moves forward, guided by the same forces that have always been at work, but now expressed across a world that is no longer one, but many, linked by the vast moving waters that fill the spaces between them. Clues to this ancient world do not lie in stories passed down or marks carved into stone by hands that once lived there. They are hidden instead in the stones themselves, in quiet details that only reveal their meaning when you learn how to listen to what rock can remember. Long after Kenorland's coastlines faded and its oceans widened into something unrecognisable, the planet kept a record of its earliest days, not in one place, but scattered across the surface of the modern Earth like pieces of a puzzle that was never meant to be easy. To step into this part of the story, imagine standing somewhere in the present, perhaps on a rocky hillside or beside an exposed cliff face. The world around you is full of familiar sights and sounds. Trees move in the wind, birds call from a distance, the ground feels solid and dependable beneath your feet. And yet within that ground there may be fragments of a world that existed billions of years before any of this took shape. The challenge is that Kenorland did not leave behind a single, intact landscape that can be visited or photographed. The supercontinent was broken apart, recycled by tectonic forces, and reshaped again and again as new continents formed and old ones sank back into the mantle. What remains are scattered survivors, ancient pieces of crust that resisted destruction and still carry the chemical and physical signatures of that distant time. These survivors are known as cratons, the most stable parts of the Earth's continents. They are thick, ancient blocks of crust that have endured through multiple cycles of continental assembly and breakup. Places like the Canadian Shield, parts of Western Australia, sections of southern Africa and regions of Scandinavia are built on these deep, old foundations. If you walk across one of these regions, you're not just walking on land, you're walking on time. The rocks in these places can be more than 3 billion years old. They formed when the planet was still settling into its early patterns of heat flow, atmosphere and life. Their surfaces have been weathered and reshaped, but their internal structures still hold information about the conditions under which they formed. One of the ways scientists learn to read this information is by looking at the minerals inside the rock. Some minerals, like zircon, are especially useful. Zircon crystals form in molten rock and can survive through immense spans of time without being completely altered. Inside each tiny crystal, atoms of uranium slowly decay into lead at a known rate. By measuring the ratio of these elements, scientists can determine when the crystal first formed. This method, known as radiometric dating, allows researchers to assign ages to rocks that reach back into the deep past. When zircons from different parts of the world show similar ages and chemical signatures, it suggests that those regions were once connected, part of the same larger landmass. Through thousands of such measurements, a rough outline of Kenorland begins to emerge. But age alone is not enough to tell the full story. The direction that ancient rocks point toward also holds important clues. When molten rock cools, the minerals within it can align themselves with the Earth's magnetic field at that time. This alignment is preserved as the rock hardens, effectively recording the direction of magnetic north as it existed when the rock formed. By studying this magnetic signature, a field known as paleomagnetism, scientists can estimate where a piece of crust was located on the globe when it solidified. Rocks from different continents that share similar magnetic records and ages may have once been neighbours, joined together before being carried apart by plate tectonics. This is how the outline of an ancient supercontinent can be reconstructed, not by finding its shape in one place, but by fitting together many distant pieces based on their hidden alignments. The process is slow and careful. Each measurement comes with uncertainty. Each data point must be compared with many others. Over time, patterns begin to appear, and those patterns suggest a picture of a world that once existed as a single connected landmass. Chemical signatures in the rocks add another layer to this picture. The composition of a rock reflects the environment in which it formed. For example, volcanic rocks that solidified on the ocean floor carry different chemical markers than those that formed on land. Sedimentary rocks that settled in shallow seas contain different minerals than those laid down in deep, oxygen-poor waters. By analysing these chemical fingerprints, scientists can infer whether a region was once part of a coastline, an interior plain, a volcanic field, or a deep ocean basin. In some ancient rock layers, there are clear signs of the Great Oxygen Shift. Banded iron formations with their distinctive layers of iron-rich and silica-rich material appear in multiple regions around the world at similar ages. This suggests that the chemical changes in the oceans and atmosphere were global, affecting vast areas of the planet at roughly the same time. These formations act like timestamps, marking a period when oxygen began to interact with iron in seawater on a massive scale. Other rocks carry the marks of ancient ice ages. Glacial deposits, such as tillites, consist of a mixture of different-sized stones and sediments that were scraped up and carried by moving ice. When these deposits are found in regions that were once near the equator, it suggests that ice reached far beyond the polar regions, supporting the idea of widespread glaciation. When similar glacial signatures appear on different continents and are dated to the same time period, it adds weight to the idea that those continents were once connected and shared the same climate system. Fossil evidence, though limited in this ancient era, also plays a role. The earliest visible fossils are not bones or shells, but the layered structures of stromatolites. These formations appear in rock layers of similar age across widely separated parts of the world. Their presence indicates that shallow sunlit seas existed along the edges of the ancient landmass, providing habitats for microbial communities. When the distribution of these fossils is mapped and compared, it helps outline the likely coastlines of Kenorland and the environments that surrounded it. Even the absence of certain features can be informative. For example, the lack of thick soil layers or plant-related minerals in these ancient rocks supports the idea that the land was largely bare, without forests or complex vegetation. The types of weathering seen in the rocks suggest chemical processes driven by rain and air rather than by roots and organic acids. This absence helps confirm that the world of Kenorland was fundamentally different from the green, living landscapes of later eras. The shape and structure of mountain belts provide further hints. When continents collide, they create long chains of folded and faulted rock. Over time, these mountains erode, but their deep roots can remain preserved in the crust. By identifying matching mountain belts on different continents and dating their formation, scientists can trace the lines along which ancient landmasses once joined. In the case of Kenorland, some of these ancient collision zones appear to link regions that are now separated by thousands of kilometres of ocean. This suggests that they were once part of the same continuous system of mountains and valleys. All of this information must be brought together carefully. Reconstructing an ancient supercontinent is not like assembling a jigsaw puzzle where each piece has a clear visible edge. It is more like trying to recreate a painting from fragments that have been scattered, faded, and reshaped over time. Each piece of evidence on its own tells only part of the story. Age data suggest when rocks formed. Magnetic data suggests where they were located. Chemical data suggests the environment they formed in. Structural data suggests how they were shaped by tectonic forces. Only by combining all of these lines of evidence can a coherent picture begin to take shape. Even then, that picture remains open to revision. New discoveries can shift timelines. Improved measurement techniques can refine dates. Additional rock samples can reveal patterns that were not previously visible. The story of Kenorland is not fixed in stone, even though it is told through stone. It evolves as our ability to read the planet's memory improves. One of the most remarkable aspects of this process is how indirect it is. There is no single rock that says, "I was part of Kenorland." There is no clear boundary that marks where the supercontinent began or ended. Instead, there is a web of connections, a network of similarities and shared histories that point toward a time when distant regions were once neighbours. This approach requires a kind of patience that mirrors the timescales it studies. Researchers may spend years analysing a single region, collecting samples, measuring their properties, and comparing them with data from around the world. The work is slow, detailed, and often uncertain, but each small step adds to the larger picture. There is also a sense of humility built into this kind of science. The deeper you look into Earth's past, the more you realise how much has been lost. Entire landscapes have vanished. Oceans have opened and closed. Mountains have risen and been worn down to nothing. The fact that any trace of Kenorland remains at all is a testament to the durability of the planet's oldest crust. This durability is not uniform. Some regions have been completely recycled, subducted into the mantle and transformed into new rock. Others have been reshaped by heat and pressure to the point where their original features are barely recognisable. The cratons that survive do so because they are thick, buoyant and resistant to being pulled back into the deep earth. These stable regions act like time capsules, preserving a record of conditions that no longer exist anywhere else on the planet. The process of finding and studying them often takes scientists to remote and rugged places. Exposed rock faces in northern forests, desert outcrops, windswept coastlines, and high mountain regions can all hold pieces of this ancient puzzle. Standing in one of these places, it can be hard to reconcile the modern world around you with the deep time recorded in the stone beneath your feet. The sounds of wind, water and wildlife feel immediate and present. The rock feels solid and permanent, and yet that same rock may have once been part of a shoreline where microbial mats soaked in an oxygen-poor sea, or a volcanic plain where lava flowed under a dimmer sun. This connection across time is one of the most powerful aspects of studying the deep past. It reminds us that the planet is not just a stage on which life plays out. It is an active participant in its own history, constantly reshaping itself and preserving traces of those changes in its structure and chemistry. The idea that we can look at a stone and learn something about a world that existed billions of years ago is, in its own quiet way, extraordinary. It means that the planet carries its own memory, written in a language of atoms, crystals, and layers that can be learned and interpreted. The work of reading that memory is never truly finished. As new tools are developed, scientists can analyze smaller samples, measure more subtle differences, and detect signals that were once hidden in noise. Isotopic studies can reveal details about ancient temperatures, ocean chemistry, and atmospheric composition. Microscopic imaging can uncover the shapes of ancient microbial structures preserved in stone. Each of these advances adds another layer of detail to the picture of Kenorland and the world it belonged to. Yet, even with all of this information, the ancient supercontinent remains partly mysterious. We can outline its rough shape, we can estimate its age, we can describe the environments that existed along its edges and in its interior, but we cannot stand in one place and see it whole. We cannot trace its coastlines with our eyes or walk from one end to the other. Its existence is known through connection rather than through direct observation. This way of knowing is fitting for a world that existed at a scale and on a timeline so far beyond human experience. It asks us to think in terms of relationships and patterns, rather than in terms of single, clear images. The stones beneath our feet become storytellers, not because they speak, but because they carry within them the results of processes that once shaped an entire planet. The echoes of that first supercontinent are still present in the modern world, not as a single, recognizable shape, but as a deep underlying structure that supports everything above it. Beneath every step you take in the modern world, there is a layered history that stretches far beyond memory, beyond language, beyond even the idea of a beginning that makes sense to a human mind. The ground feels solid and dependable, something you can stand on without thinking twice. Yet hidden inside that firmness is a record of time so vast that it turns years into moments, and moments into something almost weightless. This is where Earth keeps its deepest memories, not in words or images but in stone. To move into this part of the story, imagine holding a small rock in your hand. It fits easily in your palm. It has a texture you can feel, maybe smooth, maybe rough, maybe warm from the sun or cool from the shade. It does not look extraordinary, and yet, within that simple object there may be a history that reaches back billions of years, to a time when the sky was different, the oceans were darker, and the land had not yet learned how to host forests or footsteps. Rocks are not just materials, they are records. Every layer, every crystal, every tiny fracture tells a story about the conditions under which it formed and the journey it has taken since. Some of these stories are brief, written in a single volcanic eruption or a short-lived river. Others unfold over immense spans of time, shaped by the slow movement of continents, the rise and fall of oceans, and the quiet persistence of life. The challenge is learning how to read them. Unlike a book, the planet's memory is not arranged in neat pages. It is scattered, folded, broken, and sometimes erased. Entire chapters have been melted back into the mantle or ground down into sediment and washed away. What remains is incomplete, but it is enough to hint at a much larger narrative. One of the simplest ways Earth records time is through layers. Sedimentary rocks form when particles settle out of water or air and build up over time. Sand, silt, and mineral grains fall to the bottom of rivers, lakes, and seas, forming thin sheets that slowly stack on top of one another. Over long periods, pressure turns these layers into stone. Each layer represents a moment, or a stretch of moments, in the planet's past. A flood might leave behind a thick, coarse layer of sand. A quiet period might produce a thin, fine layer of clay. A change in ocean chemistry might create a band rich in a particular mineral. Stacked together, these layers become a timeline you can see and touch. In some places, this timeline stretches back only a few million years. In others, especially in the ancient cores of continents, it reaches into the deep past, toward the time when Kenorland still existed. But layers alone do not tell you how old something is. They tell you what came before and what came after, but not how much time passed in between. For that, you need a different kind of clock. That clock is built into the atoms themselves. Certain elements are unstable. Over time, they change into other elements at a predictable rate. Uranium slowly decays into lead. Potassium decays into argon. Rubidium decays into strontium. These processes happen inside minerals, ticking away like microscopic hourglasses. When a mineral forms, it often traps some of these unstable atoms inside its crystal structure. From that moment on, the clock starts. By measuring how much of the original element remains and how much of the decay product has formed, scientists can calculate how long it has been since the mineral solidified. This method allows ages to be assigned to rocks that are billions of years old. One of the most important minerals for this purpose is zircon. Zircon crystals form in molten rock and are incredibly durable. They can survive being eroded, transported, buried, heated, and even partially melted, all while preserving the atomic clock inside them. Some of the oldest zircons ever found date back more than 4 billion years, to a time when the Earth itself was still in its infancy. These tiny crystals are like time capsules, carrying information from a world that no longer exists in any recognizable form. Through the study of zircons and other minerals, a timeline of the planet begins to take shape. It becomes possible to say not just that one layer is older than another, but that it formed 2.7 billion years ago, or 2.4 billion years ago, or at some other point in deep time.
This precision turns stone into something like a calendar, marking out the long arc of Earth's history. But time in rocks is not always straightforward. The planet is active. Heat, pressure, and movement can reset the clocks in minerals. A rock that formed billions of years ago can be reheated during a mountain-building event, causing its atomic clock to start over. Layers can be folded, tilted, or turned upside down. Entire sequences can be broken and carried far from where they originally formed. This means that reading Earth's memory is not just about measuring ages. It is about understanding context. Where was this rock formed? Was it deep underwater or on land? Was it part of a volcanic eruption or a quiet sedimentary basin? Has it been heated, squeezed, or moved since then? To answer these questions, scientists look at the textures and structures inside the rock. The size and shape of mineral grains can reveal how quickly a rock cooled. Large, well-formed crystals often indicate slow cooling deep underground. Small, fine grains suggest rapid cooling at or near the surface. The presence of certain minerals can indicate the temperature and pressure conditions during formation. Some minerals only form under extreme heat and pressure, deep within the crust. Others form at the surface, in the presence of water and air. Even the way layers are arranged can tell a story. Tilted layers might indicate that the rock was once horizontal and later pushed upward by tectonic forces.
Folded layers can reveal the direction and strength of those forces. In this way, each rock becomes a kind of witness, carrying multiple lines of evidence about its past. When these individual stories are compared across wide regions, patterns begin to emerge. Rocks of similar age and composition appear in places that are now far apart. Mountain belts on different continents show matching structures and timelines. Sedimentary layers deposited in shallow seas show up in regions now separated by oceans. These patterns suggest that the land was once arranged differently, that pieces now distant were once close neighbours. This is how the memory of Kenorland and other ancient supercontinents is traced forward through time. The story does not stop with the breakup of a single landmass. The same processes that brought Kenorland together and pulled it apart continue to operate over and over across billions of years. Later supercontinents formed. Rodinia gathered and broke apart. Pangaea came together and then divided into the continents you recognize today. Each cycle left its mark in the rock record, adding new layers to the planet's memory. These cycles are not perfectly regular. They do not follow a simple schedule. Sometimes continents remain together for hundreds of millions of years. Sometimes they separate more quickly. The reasons lie deep within the planet, in the complex patterns of heat flow and mantle movement that are still not fully understood. Yet through all of this, the rocks continue to record what happens. In some places, you can see this memory laid out like a vertical timeline. A cliff face might show dark volcanic rock at the bottom, formed when lava flowed across the surface of an ancient land. Above it, lighter sedimentary layers might mark a time when the area was covered by a shallow sea. Higher still, different layers might indicate rivers, deserts, or ice. Each band is a different environment, a different chapter in the story of that place. Even in regions where the record is more broken, where layers have been folded or eroded, clues remain. A single unusual mineral can hint at a past event. A thin layer of ash can mark a distant volcanic eruption. A change in the type of sediment can signal a shift in climate or sea level. The memory of the planet is written not just in grand, obvious features, but in small, subtle details. Isotopes add another layer to this memory. Atoms of the same element can come in different forms, known as isotopes, which have slightly different masses. The ratio of these isotopes can change depending on environmental conditions. For example, the ratio of different oxygen isotopes in a mineral can reveal information about the temperature of the water in which it formed. Carbon isotopes can hint at the presence and activity of life. Sulfur isotopes can reflect changes in the chemistry of the atmosphere and oceans. By measuring these ratios, scientists can reconstruct aspects of ancient climates, ocean chemistry, and even biological activity. In the context of Kenorland, these isotopic clues have helped confirm the timing and extent of the Great Oxygen Shift. Changes in sulfur isotopes, for instance, mark the point when oxygen became abundant enough in the atmosphere to alter how sulfur compounds were processed on a global scale. This kind of evidence ties together the stories told by rocks, water, air, and life. One of the most striking things about reading Earth's memory is how interconnected everything is. A change in the deep mantle can lead to volcanic eruptions. Those eruptions release gases into the atmosphere. The atmosphere influences climate. Climate affects how rocks are weathered and how sediments are deposited. Those sediments become new rocks, which one day may be buried, heated, and transformed again. The planet is not a collection of separate systems. It is a single, evolving whole, and its memory reflects that unity. There is also a sense of scale that comes with this perspective that can be difficult to hold on to. Human history, with all of its complexity and drama, fits into the thinnest possible layer at the very top of this record. The rise and fall of civilizations, the development of languages, the building of cities, all take place in a span of time that is almost invisible when compared to the billions of years recorded in stone.
Even the appearance of complex life of plants and animals occupies only a small fraction of the planet's total history. Most of Earth's story is microbial, geological, and chemical, unfolding in ways that are slow, patient, and largely unseen. This does not make the human chapter unimportant. It simply places it in a broader context as one moment in a much longer narrative. The idea that rocks can hold memories of worlds that no longer exist can feel abstract at first. But when you begin to notice the details, it becomes something more tangible. A ripple mark in stone can reveal the direction of an ancient current. A layer of rounded pebbles can show where a river once flowed. A band of unusual color can mark a change in the chemistry of the sea. These are not symbols or metaphors. They are physical traces, direct results of processes that happened long ago. In some cases, these traces are so well preserved that you can place your hand on them and feel the shape of something that existed hundreds of millions or even billions of years before you were born. This connection across time is one of the quiet wonders of studying the Earth. It is not about finding a single dramatic moment or a clear, simple story. It is about learning to see patterns in complexity, to recognize that what looks like a static landscape is actually a snapshot in an ongoing process of change. The rocks beneath your feet are not finished. They are part of a cycle that continues right now.
Sediments are still being deposited in rivers and oceans. Mountains are still rising and eroding. Volcanoes still bring material up from the deep interior. Plates still move, slowly carrying continents toward new arrangements. The memory of the planet is still being written. When future observers, whoever or whatever they may be, look back at this moment in Earth's history, they will find traces of it in stone. Layers that record the chemistry of the air you breathe. Minerals that formed in the water you drink. Sediments that settled in the rivers and seas that exist today. Your own time will become part of the deep record, just as Kenorland's time is part of it now. This perspective can feel both humbling and grounding. It reminds you that you're part of something much larger than a single lifetime or even a single species. The same processes that shaped an ancient supercontinent and recorded its existence in stone are still at work, shaping the world you live in now. As the pieces of Kenorland became the foundations of later continents, they carried their memories forward, layered over by new stories, new environments, and new forms of life. Those layers are still there, waiting to be read by anyone willing to look closely enough. The rocks remember, and through them, the world continues to speak, quietly and steadily, across the immense distance of time that still stretches ahead. This moment, right now, is a thin and delicate edge between an immeasurable past and an unknowable future. After drifting through billions of years of shifting stone, changing skies, dark seas, and quiet microbial worlds, the story of Kenorland gently releases its hold on your imagination and guides you back toward the place where you're sitting, lying down, or simply listening. There is no sudden jump, no sharp return, just a gradual reappearance of the present, like a shoreline coming into view through morning mist. If you take a breath and notice the air around you, it feels ordinary, it feels easy. The oxygen fills your lungs without effort. The temperature is likely comfortable enough that you do not have to think about it. The light, whether from a lamp, a screen, or the fading glow of evening, falls softly across the space you're in. All of this feels simple, and yet every part of this moment carries the deep history you have just travelled through. The oxygen in that breath was not always here. It was built, slowly and patiently, by countless generations of tiny organisms living in shallow seas under an ancient sun. The metals in the walls, the floor, the device playing this sound, and even the wiring hidden behind it were once dissolved in oceans that looked nothing like blue, carried by rivers across a bare supercontinent, and locked away in rock when the planet learned how to rust. The ground beneath you, whether it is soil, concrete, or stone, rests on layers of crust that have been assembled, broken apart, and assembled again through cycles of supercontinents you will never see in a single shape. Kenorland was one of the first of those cycles, an early attempt by the planet to gather itself into something whole, before learning, once again, how to let itself come apart. Returning to the present does not mean leaving that world behind. It means recognizing that it is still here, quietly woven into everything around you. The continents you know today, with their familiar coastlines and names, are distant descendants of those ancient pieces of land. The oceans that separate them carry water that has been cycled through the Earth system countless times, evaporated into the air, fallen as rain, frozen into ice, and poured back into the sea through rivers and melting glaciers. Even the sky above you, with its blue colour and drifting clouds, is a product of that long chemical journey, from a world without oxygen to one where the air itself supports forests, animals, and human thought. If you look around the space you're in, you might notice small, quiet details. The texture of a wall, the pattern of light on the floor, the sound of something distant, a car passing, a breeze through a window, a clock ticking somewhere out of sight. These are ordinary signals of the present moment,
But they exist in a world shaped by processes that began long before any of these sounds or structures were possible. The idea of now can feel solid, like a point you can stand on. Yet when you stretch your view across deep time, it becomes more like a moving line, sliding forward through a vast landscape of past and future. Kenorland lies far behind that line, almost unimaginably distant. Still, the effects of that ancient world continue to ripple forward, shaping the conditions that make this moment possible. The story you have been drifting through is not just about a place that no longer exists. It is about how a planet learns. It learns how to build an atmosphere. It learns how to regulate its temperature. It learns how to cycle materials between its deep interior and its surface. It learns how to create spaces where life can not only survive, but slowly grow more complex. Those lessons are still being applied. The Earth has not finished changing. The continents are still moving, even now at speeds too slow to notice without careful measurement. Mountains are still rising in some places and wearing down in others. Rivers continue to carve valleys. Sediments still settle on the seafloor, forming the layers that will one day become new rock. The atmosphere still shifts as gases move between air, water, land, and life. The climate still responds to subtle changes in sunlight, chemistry, and circulation. The planet remains, in every sense, a work in progress.
There is something grounding in realizing that the world beneath you is not static. It is not a finished product. It is part of a continuous process that has been unfolding for billions of years and will continue long after this moment has passed. Your own life, measured in decades rather than eons, sits within that process like a brief bright thread woven into a much larger fabric. This perspective does not make the present smaller. If anything, it makes it richer. The simple act of resting, listening, or breathing becomes connected to a story that stretches back to the earliest days of the planet. The quiet of the room becomes part of the quiet of ancient plains. The rhythm of your breath echoes in a distant way, the rhythm of tides under a closer moon, and the rise and fall of oxygen in a sky that was still learning how to be breathable. You do not need to hold all of that in your mind at once. It is enough to let the idea sit gently in the background, like a distant horizon you are aware of without needing to stare at it. If you think about the path of a single atom, the connection becomes even more tangible. An oxygen atom in the air you just inhaled may have once been part of a water molecule in an ancient sea. That water molecule may have been split by a microbe using sunlight to make energy. The oxygen may have drifted into the air, reacted with iron, sunk into the seafloor, been buried, turned into rock, and later released again through volcanic activity. The atom's journey could span billions of years, crossing oceans, continents, and layers of the planet itself, before becoming part of this moment. Every breath you take is part of that ongoing cycle. The same is true for the carbon in your body, the calcium in your bones, the silicon in the glass of a window, and the metals in the ground beneath you. They all have deep histories that reach back into the world of Kenorland and beyond, into the earliest chapters of the Earth's formation. Returning to the present does not mean leaving those histories behind. It means recognizing that they are still active, still moving, still shaping the world in ways both subtle and profound. As you settle into this awareness, there is no need to rush forward to what comes next. The story of the planet does not demand urgency. It unfolds at its own pace, steady and patient. Regardless of how quickly or slowly you move through your day, the same can be true for you, at least in this moment. You can let your thoughts drift, much like the continents themselves, moving gently without a fixed destination. You can allow the ideas of deep time, ancient seas, and shifting skies to fade into the background, leaving behind a sense of connection rather than a list of facts. The world you live in is layered, not just in stone and sediment, but in time. Every place you go has a past that stretches far beyond its current shape or name. Every landscape has been something else before, and will be something else again. Even the quietest, most familiar spaces are part of a much larger story of movement and change. If you're near a window, you might notice the sky outside. Clouds moving slowly, stars beginning to appear. The fading of daylight or the first hint of morning. These simple, everyday sights are part of the same system that once cast light over Kenorland's bare plains and oxygen-poor seas. The sun you see is the same star, older now, brighter now, but still following its steady path across the sky, just as it did billions of years ago. The moon, too, still rises and sets a little farther away than it once was, still guiding the tides, still shaping the rhythm of the planet in quiet, persistent ways. These familiar motions link your present moment to that distant past in a way that is both simple and profound. You do not have to understand the details of plate tectonics, atmospheric chemistry, or microbial metabolism to feel that connection. It is enough to know that the ground beneath you and the air around you are part of something that has been evolving for an almost unimaginable length of time. The story of Kenorland, and of all the worlds that came before and after it, is not just a story about the Earth. It is a story about continuity, about how change does not erase what came before, but builds upon it. The ancient supercontinent is gone, but its pieces remain, forming the cores of modern continents. The oxygen-poor sky has been transformed, but the processes that changed it are still active. The microbial mats of shallow seas have been joined by forests, animals, and cities, but the foundation they laid continues to support the living world. In this way, the past is not behind you. It is beneath you, around you, and within you. As this long journey through deep time gently comes to rest, there is no need for a sense of ending. The planet's story does not conclude. It simply moves on, carrying forward everything it has learned, everything it has built, and everything it has changed. Your own story, in its own way, does the same. The next breath you take, the next step you make, the next thought that drifts through your mind will all become part of the ever-growing layer of the present that future moments will one day look back on as the past. For now, you can stay right here, in this quiet point between what has been and what will be. Let the weight of deep time settle gently, not as something heavy, but as something steady, like the ground itself supporting you without asking for anything in return. The world continues to turn, the air continues to move, the oceans continue their slow, endless circulation.
And somewhere, far beneath the surface, the deep processes that once brought Kenorland together and then pulled it apart are still at work, shaping a future that will one day become another layer in the long, patient memory of the Earth.